Hi everyone. I can see some familiar faces. It's nice to see you, and I hope everyone is doing okay. I am going to start today by talking about fracture of sea ice by ocean surface waves in CSM3. This is work that I've been doing a little bit on recently, but with big contributions from Bruno Tremblay, Cecilia Bitz, Dave Bailey, and more in our little wave ice group. So this work has been motivated by the enhanced ocean surface wave activity that we've been seeing in the new Arctic, as the Arctic Ocean has become increasingly ice-free and more open water areas have opened up. This has enabled a growth of waves. And so here we see wave heights in the Beaufort Sea from 1990 to 2018 from Thompson et al., highlighting this increase in waves. And this is something that has direct impacts on Arctic communities, on things like storm surge and coastal erosion. Then in the Antarctic, we know that this is subject to large spells where waves are able to grow over the whole Southern Ocean. And these increasing waves could be important in terms of a potential wave ice feedback. So the basic idea being that waves can travel through sea ice.
Letty, sorry to interrupt. All of a sudden it stopped sharing yours. The screen just stopped.
Okay.
We can hear you though.
Is that okay?
Yes, it's back. Thank you.
So waves can travel through sea ice, especially through areas of thin sea ice or broken up sea ice. They can also be generated locally by winds in sea ice covered regions. Waves can fracture sea ice, breaking it up into smaller flows, and then this fragmented sea ice can melt faster, which could lead to further increased waves. And so this has been the basic motivation for this wave ice work, but there are a number of challenges here. The first challenge being that many of these, there are many different processes that affect the fragmentation of sea ice that then determine the flow size distribution. So besides wave fracture, we also have thermodynamic processes such as new ice formation, lateral melt, lateral growth, and the freezing together of flows. These are the main processes that we considered in the modeling work, but you can also think of other processes in the real world that likely depend on flow size and can feed back on flow size. And then the second main challenge has been that observations are very limited. Flow sizes span across a wide range of spatial scales, and it's really difficult to capture this in observations. There has been a lot of progress in this area, and at the right, I'm showing a figure from Ellen Buckley's study where they developed an automated tool to segment flow sizes and pull them out from imagery. But
I'm sorry to interrupt again, but it just stopped again. I don't know if it's like when you switch slides or something. I'm so sorry.
Oh, that's okay. I'm sorry if it's on my end. I think you see this now.
Yep, that looks right.
Okay. So because it's difficult to make these observations, we don't really have data sets spanning whole basins and different seasons, making it hard to tune basin scale models. So what we've aimed to do in this wave ice modeling work is to develop physically realistic processes as much as we can. And so now in SEIS, this is work that has been built up over a number of years, building off theory developed by Chris Horvath and Ellie Zipperman in 2015. I then, with co-authors, implemented this joint flow size and thickness distribution into the SEIS sea ice model, where flows are near circular, and we represent the flow size distribution with discrete size classes, such that in each grid cell in the model, a fraction of the sea ice concentration belongs to different flow size classes, as well as different ice thickness classes, as in the normal sort of typical version of SEIS. And so then this joint flow size and thickness distribution can involve subject to advection, which is the first term on the right, thermodynamics, mechanics, and then additionally wave fracture. And I can see it stopped again, so I'm going to reshare. Sorry about that.
I don't know what happened, but thank you.
So then with each, we simulate this. No?
Do you see that you're in an infinite mirror? Do you want us to share it from this end, and I can just advance slides if you
Yeah.
want?
I
Okay.
think so. Do you have it there?
Yep, he's gonna pull it up. Hold on. I'm sorry about the technical stuff. Okay.
Oh, okay, great, thanks. And then advance, please. So then in each grid cell, here I'm showing for the Arctic on average, but within each grid cell, we're simulating then a sub-grid scale distribution of flow sizes, also within each thickness class. So that we capture this broad distribution of flows, as you see here in this figure. Next slide, please. So now what we have more or less beginning to become available is a coupling between the waves and sea ice that's occurring through the flow size distribution now in CSM3. This includes the WaveWatch 3 wave model working on the MOM ocean grid, a attenuation scheme that describes how the ocean waves are influenced by sea ice as they travel through the sea ice zone. And this includes a dependence on flow size, thickness, and concentration. So the ocean wave model and sea ice model are exchanging the mean flow size, thickness, concentration, and wave spectrum. And we've now started running this in large-scale simulations, and with minimal changes. The only thing that we've really tuned so far is the flow welding parameter. Next slide, please. One more. And then in the course of developing the flow size distribution model, we've realized that there were some limitations to the scheme that's currently included in the SICE model, which was developed by Horvath and Zipperman. The scheme assumes that the sea ice flexes perfectly with a sea surface height field, which can be a reasonable approximation in some cases. And then they calculate the strain based on a very large flow, and apply that then to a flow size distribution. And in this parameterization, there's also a computation where we find the extrema in the sea surface height field using finite differences. Next slide, please. But now we have, led by Bruno Tremblay, worked on a new scheme for the wave fracture, which I'm abbreviating here as B25. Which doesn't include this assumption about flexibility. So there's no assumption that the sea ice is perfectly flexible or perfectly rigid. And instead, we solve a conservation of momentum equation for a thin elastic plate in hydrostatic equilibrium. And this is something where we are taking flow size into account. So this strain field is really calculated for each flow size. Next slide, please. Oh, sorry, I can do this back one, please. So then in both of these schemes, we're looking at these strain fields on a one-dimensional spatial domain, and we find locations where each strain exceeds, induced by the waves, exceeds a critical strain, and then we compute the fractures at these points. And then by iterating this over different sea surface height field realizations, we compute a fracture histogram that we then use to evolve the flow size distribution. Advance, please. In the new scheme, and here is an example just showing for one flow with a diameter of 200 meters and a thickness of 1 meter, with some prescribed wave field applied to it. Compared to the previous scheme, we find now that the strain values are generally smaller and much closer to observations. So here in this figure, the red lines show this critical strain of 3 times 10 to the minus 5, which has been determined by field observations. And so we see that the strain is exceeded, this critical strain is exceeded at just a few points, and then the flow can break at these locations, and then we can update our flow size distribution based on these distances. Next slide, please. And then we've looked at the impact of including this new wave fracture scheme now in the global model. So I should caveat that these results are very preliminary. This is just from a short trial simulation using a data atmosphere configuration of CSM3. So it's the G comp set. And as I mentioned before, we've taken the SEISS implementation, but we have tuned this flow welding parameter. And when we compare the two different wave fracture schemes, so on the left is the current implementation in SEISS, Horvath and Simpson in 2015, and then at the right is the new scheme developed by Bruno. We can see that in this second case, which we think is the more realistic case, we also increase the representative radius of the flow. So the sort of mean flow size, especially in Antarctica, is larger in this simulation, and we think this is somewhat more realistic than the previous scheme. Next slide, please. Then also, if we look at the number distribution, so this is for the Antarctic as in total across the whole hemisphere in September. The left shows the current wave fracture scheme, and the right shows the new wave fracture scheme. And so you can see that here the slope of the flow size distribution is quite a bit less steep in the new case, and we have more flows of large sizes across a variety of these different flow size classes. Next slide, please. So to summarize, we are now able to represent coupled wave sea ice interactions via the flow size distribution in CSM3. So this is including the physics to represent the thermodynamics that shape the flow size distribution, as well as the wave fracture. We found that the FSD simulation appears reasonable with minimal tuning. This is really without having access to a good observational data set that we can use to really quantify this, but we certainly see the things to sort of first order look reasonable. We have worked on a new wave fracture scheme, which is more physically realistic and appears to improve the Antarctic flow size distribution with less impact in the Arctic. And then there's much more to do. So in terms of the wave fracture, we'd like to see where we can simplify this scheme and learn more from it in terms of the kind of physical dependencies on ice thickness and flow size. There's more work to be done to test this further in the fully coupled CSM3. We are running some simulations with this turned on with the fully coupled atmosphere as well, but there's more work to do to check the impact in those simulations. And then we'd also like to work towards evaluating the simulation of the flow size distribution against observations, which would be in more case study simulation. So whether data atmosphere or wind nudging to try and reproduce more kind of individual storm events and look at how the flow size distribution changes in those. I'd like to end by thanking you for letting me join remotely, and also thanks everyone who has participated in this wave ice group again. And I'm happy to take any questions.
Thank you so much, Letty. Questions in the room or online? All right, Kevin. And yeah, Ruth mic should be on.
And what prospects are in the next few years for having enough observations to constrain your system in a way that satisfies?
Yeah, that's a great question. So I think that it may be possible to do more with the current observations that we have, but when we so for various reasons, we haven't really had access to this, this setup before. But now that we have this whole physics in the new version of the model, I think with this version now, we could do more to look at these sort of case study efforts. And there, I think we can go to these regions where we already have observations, and in a more constrained setup, so whether it's the data atmosphere or the nudge winds, we can look at more specific events based on observations that are already existing. In terms of future observations, I know that there is work going on, but this isn't something that that I myself have been working on, and there's maybe others here who can speak more to that.
I have a follow-up question too, if you don't mind.
Yeah.
How long is a typical case study where you can get some useful results?
Well, I would think that what I would plan to do is to sort of branch off some short simulations and look over a single season. There are a few observational studies that have mostly in the summer some a few different months of observations. And so I think to get some initial evaluation, I think that would be sufficient.
Great, thank you.
Thanks.
All right, any other questions in the room or online?
I was just going to ask, this is Alec. Why do you see that increase in frequency for very high radii? Is that something to do with grid size or something? Or?
Yeah, so this is the impact here I'm showing of the new wave fracture scheme. Is this what you're, so if I go back to
Oh, just at the end, it kind of increases for the very high flow radius.
So this flow size category has to include all larger flow sizes. So we always have some sort of accumulation of flows in this large size category just because we've discretized this distribution.
I see. Cool, thanks.
Yeah.
And move on to the next presentation. Our speaker will be Will Gregory. What's up in front? Yep. And you should be able to just go there.
Okay, great. Yeah, thanks for having me here. It's great to be in Boulder for the first time and visit NCAR. It's been a really wonderful experience getting to chat to you all, and I'm going to be sad going back to New Jersey after getting exposed to the view you get every day here at NCAR. So yeah, I'm a postdoc at GFDL, and I'm going to talk through some of the work I've been doing over the last couple of years trying to develop a machine learning scheme to do sea ice bias correction in the GFDL coupled climate model. And I hope some of these kind of takeaways could be used in CSM also. So yeah, this is some work I've been doing with folks there, Mitch Bushuk, Yongfei Zhang, Alistair Ackroft, and Laura Zanner. Just to motivate a bit, this is a figure from Letty's paper showing just the spread in sea ice area in the Antarctic across CMIP6 models. I always find this figure pretty striking in terms of just the actual spread we get across these models, and in particular, some models showing lower sea ice area even in winter than the observed summer sea ice area, and just showing that individual models can show considerable biases in the sea ice mean state, and we know these models are biased for various reasons, and when we look at the kind of breakdown of what contributes to model physics bias and uncertainty in terms of future projections, this is a figure from Dave Bonan's paper. We see that model physics makes up a sizable contribution to future uncertainty in sea ice area projections. And the work I'm funded under, that's called this M Squared Lines project, is a commit-funded project where we're really trying to use machine learning to target these model physics errors specifically and reduce surface biases in these models. And the way that we're doing that is through two parallel threads. On the one hand is trying to learn new subgrid closures, typically from high resolution simulations. So you can think of like an eddy resolving model for the ocean, and we're able to extract the subgrid forcing that we're missing in the coarse resolution simulation and learn that as a kind of tendency that we use to improve the models and improve the large scale statistics that we're missing. And then in this parallel path, which is what I'm going to be talking about today, is whether we can learn these errors within the coarse resolution simulations themselves through DA. So can we use the observations to actually tell us something directly about the errors in the coarse resolution model? And then we feed these back in, hopefully in the end, with some great looking hybrid model. So we're doing this through DA. This slide here is just a simple schematic about what happens in a DA process or a typical DA process. So we can see this distribution. This distribution on the right here, this pink distribution is showing our kind of initial estimate of what the climate state might be. We can think of this as, for example, sea ice concentration. We have an ensemble prediction, so we have some distribution. And then depending on what the observations are, with also some uncertainty, we produce this updated climate estimate or our new kind of posterior state based on what the observations are after we've done DA. And so based on what our prior estimate was and what our new estimate is, we've basically shifted our distribution using this correction or an increment that we get from DA. And so there's been a lot of literature, especially from NWP community, about how these corrections, these short-term corrections that we're applying to the model, are indicative of the systematic model biases. And we can see this here in the GFDL model. If we compute the time mean of these increments from DA, these kind of fast physics errors, which is the bottom plot on the right, we can see that those map really closely onto the systematic long-term bias of the model. And this kind of indicates that there's some errors that are accumulating over these short timescales that are really telling us something about bias processes within the model. And what we're trying to do with M-squared lines is see if we can actually learn a state-dependent representation of this model error. So can we use information effectively from this pink PDF to tell us something about, allow us to predict this correction, so independent of any observations. And I'm going to show some results of where we've done that in both isocean configurations, so force from reanalysis, and then also in the coupled model. So just to look at, how well the network actually does at predicting these increments. So these are some snapshots in the Arctic and Antarctic, and we're using the same network to do this across the whole globe. So the left are what the DA increments are. When we show the model what the observations are, we produce a correction, and then on the right is what the machine learning model predicts using only model state variables. We can see that those agree really well, especially in the Southern Ocean. We've got a lot of kind of local scale variability, which the machine learning model is able to get really well. And then, taking a time mean of all of these predictions and seeing how well do we produce the mean increment in both hemispheres, and we can see they agree really closely, which suggests we may be able to use this to improve the model if we implement these corrections online. And that's generally what we find. So this is a plot showing some snapshots on the top and a mean bias on the bottom. On the left is the free-running isocean model, so still reanalysis force, and we can see the model generally has some ice edge errors. This is the observed ice edge contour, so positive means red values mean positive biases. And with DA, we clean up a lot of that errors we would expect as we've told it what the observations are. And then our machine learning model is also tidying up those errors really well. And we're able to sizably reduce the kind of the long-term bias. This is a 5-year simulation, so not exactly a climatology, but overall reducing the bias. And we see a similar story in the Arctic. Not as effective as in the Antarctic, but still reducing those errors really well, especially around the ice edge. This is a snapshot in summer in the top, and again, the climatology in the bottom. Okay, so we found that it works pretty well in the isocean model. We're able to reduce the biases over this 5-year simulation in both the Arctic and Antarctic using a single neural network that kind of generalizes to the whole globe. So that was great. And we really wanted to see, can we actually apply this in a fully coupled model running freely, doing some reforecasts. So this is still work in progress, but we've made some strides in the right direction. And yeah, I wanted to show this today. So if we apply this neural network just kind of out of the box, this is for a March initialized forecast. On the top here is the kind of, we're doing this in a 1-year reforecast. So this is the kind of 12-month bias from SPEAR. This is the kind of operational configuration of the model. So positive bias is generally around the kind of ice edge locations and some negative biases in places like Hudson Bay. And when we apply the machine learning model, we make it worse. So the red here, this is the response to the machine learning model. So red means we've made the model worse. We can see here things like the spatial probability score and then the RMSE. Coming into kind of the summer months, we've made the predictions of the ice edge worse, and also the kind of overall RMSE worse. Not good. And if we look at the Southern Ocean, what's happened there? Even worse. So SPEAR has pretty sizable positive biases. Are kind of, yeah, we've got much more biased sea ice state in the Southern Ocean than in the Arctic. And what's happening when we implement our machine learning scheme is that, yeah, again, coming into summer, we really exacerbate some of these biases. So thinking about what's going on here, we kind of went back and thought, maybe this is obvious, but at the time, we didn't think so. We learned the biases originally in our machine learning approach based on this isocean configuration of the model where we're forcing from reanalysis. And then that's what the biases look like in the Southern Ocean in that configuration of the model. And on the right is a different configuration of the model, which is the coupled model, but we're still nudging the atmosphere in this approach. So it's a pretty strong nudging. We're nudging at 6-hourly timescales, but the ice and ocean configurations are the same. And we can see these have pretty different bias patterns in these two configurations of the model, which may suggest that we're missing some information about the atmosphere ice fluxes that the machine learning model hasn't been exposed to. And if we look at the increments that we get from DA from both of these configurations of the model, we can see they're pretty different. So generally, we have a slight negative bias in place like the WED-LC, so a positive bias, sorry, so the DA is trying to reduce the bias there. Whereas in the coupled model, we need to actually add CIs in that location. So if we go back and rerun our reforecast experiments where we train the machine learning model on increments derived from the coupled model, we actually do see some improvements in this March initialized reforecast. These kind of pink curves here showing that, relative to the free-running SPEAR model, we're reducing these biases over this year-long period. And similarly, in terms of, spatial probability score and RMSE. In the Southern Ocean, overall making the model better. There's some issues going on at the end of the forecast year coming into the summer again, which we've got some theories about what might be going wrong there, but we think there's some kind of interactions with ocean biases. We've still trained the model in a nudged configuration of the model because we're really trying to get at sea ice physics errors here. But there's going to be some coupled model errors that are interacting with our scheme here, which we're not accounting for, and there's probably issues with that going into the summer. But we were pleased to see that this kind of hypothesis holds relatively true, that we need to kind of incorporate some information about the atmosphere in our training to be able to generalize well into these reforecasts. And then this is just kind of looking at different months. So we've run this for 3 different initialization times at the minute, so March, July, and November. So we can see for different target months and lead times. This is for the machine learning model trained in the ice ocean configuration. In the Arctic, we generally make the model worse after a few months, and then considerably worse in the Southern Ocean. And then with our coupled model, we're generally improving the model over that the ice ocean configuration pretty much for all times in the Arctic. And like I said, we had some issues kind of coming into the summer in the Antarctic that we're still working out. So lastly, I just want to kind of talk about how this could be kind of translated over to CSM. A lot of the code that we've built for this DA training and implementation is pretty generalizable, and the CIS component of SPEAR and CSM are not too dissimilar. So there's a lot of code bases here, which I think could be taken pretty much off the shelf and used in CSM. We've written our own data assimilation code in Python, which is just a few hundred lines of code, which you can basically just plug into the model and do CISDA with the Kalman filter method, and some code to do machine learning training in PyTorch. And then we've implemented this bias correction into the source code of SIS2, which through a bit of work could go into SICE, but I hope not too much work. If you're interested in more of this, the results on the kind of initial implementation into the ice ocean model, we've published in 2 papers. And also, if you know this guy, Will Chapman, he's not here. He's done a lot of work on this in CSM already, doing the similar approach, but for the atmosphere. So, he's really got into the nuts and bolts of how to get machine learning models, bridged with Fortran and CSM. So if you see him walking around NCAR and you're interested in this, then definitely grab him and talk to him. But with that, I'll stop there and I'll leave that up.
In the room, online. Start with Elio.
Nice work. One thing that's not clear to me is this only looking at the ice, so it's trying to learn the data simulation errors in the ice and not also in the atmosphere and ocean.
Yeah, exactly. So that was our motivation for doing the initial training in this forced configuration of the model with SSTs being nudged. We were trying to simulate an environment where we've got a perfect atmosphere and good ocean. So the increments that we're getting from DA are intrinsic sea ice model physics errors, and that's not really true. But we were hoping that would work, and we find that it doesn't really work. I think some future work that we're kind of looking into is where I think the best way to do this would be to do DA in all 3 components and learn consistent increments across the system. And then you kind of learn the systematic intrinsic model errors in each component, but also the coupling errors and fluxes that you need to also include.
Marika.
So, well, nice talk and nice work. In your nudged atmosphere, is that a full data assimilation for the atmosphere, or is it, just nudging the winds?
Yeah, it's just nudging the temperature, winds, and humidity, I think.
Down to the surface?
Yes.
Okay. So it's a fairly tightly constrained atmosphere. So it seems like it would be really interesting to look at your forced run, your coupled run, to try and learn more about the feedbacks and
Yeah.
where there's impactful feedbacks for the sea ice. And have you thought about doing that, or are there
Yeah, we've gone back and
plans
forth.
to do that?
Yeah, we've gone back and forth a lot on that in terms of what would be best. And I think, for the ocean, for example, in their DA configuration, they have a free running atmosphere and find that that's best to get the best kind of result out of the ocean DA. And for us, we found that having the winds right gives us the right kind of sea ice thickness pattern in the Southern Ocean. So that's so nudging is kind of really important for that. But we are just running different tests at the minute to see what impacts have, a free running ocean atmosphere, a nudged atmosphere. And yeah, whether, we relax the nudging timescales as well, I think could be indicative just to tell us how does the sea ice respond and what kind of how does that change the bias patterns and so on. But yeah, it just means running a lot of expensive simulations, and I'm already using up all of Jeff Deal's quota anyway. So
Questions online? Just want to make sure. All right, David.
Yeah, great talk. And so part of your motivation was to identify incorrect sea ice physics, as I understood it.
yeah,
What do you have any results on what sea ice physics do we need to change?
short answer is no. And that's been, something we've just been kicking down the road kind of continuously throughout this project. And I think it really needs a revision of the approach altogether. I think these DA increments are accumulating the errors of all of the errors in the model physics. So to be able to piece out, is this an error in the sea ice rheology, or a parameterization of the surface albedo, or a couple model physics error. We haven't really figured out a good way to do that. I mean, there was some literature that was doing that in NWP from Tim Palmer's group at ECMWF, and they were doing it kind of through different perturbation experiments, and it isn't clear how we can translate this into this approach of doing it through machine learning. We tried to do it through tendency decomposition and looking at mass budget terms in the CIS, but it's hard to really attribute to the corrections to and account for compensating biases and things like that. It's I think you might. I'm kind of wondering how how useful it would be to do DA and things like parameter estimation, and you can learn errors related to parameters, and does that tell you something more about the errors in the physics. But yeah, we're a long way off from that yet. So we've kind of gone down this rabbit hole of thinking, okay, we've got something which maybe we can just improve the forecasts in the model and learn something hopefully about training models in training machine learning models in coupled models, and kind of find some takeaways from that.
Thank you, Will. We're gonna move on to the next presentation, which is Alec Petty online. Are you able to share your screen, Alec, or do you?
Yeah, I think so. Let's see.
We can hear you just fine.
Me.
If you need us to, we can share it here, and I'll just advance it for you.
Okay, give me 1 second. It might be easier for you to do it because I'm having some permission. That's okay.
Go ahead and do that.
That.
All right, go ahead and start with Petty.
Oh, great. Yeah, so thanks very much. This is a follow-on from a talk I gave last year to the same meeting. Hopefully we've made some decent progress and address some of the comments and feedback from last year's presentation. Thankfully, this work is now finally sufficiently advanced to generate this publication that should be appearing in GMD as a preprint any day now. If you do want a PDF, please do reach out. This is work that's undertaken in close collaboration with Chris and Maddie. Chris especially generated virtually all of the plots that I'll be showing today. So thanks very much to him. Next slide. Similar to Will, we're motivated by uncertainties in sea ice projections across both hemispheres and ways that we can reduce that model uncertainty. Next slide. Various methods that have been proposed to kind of deal with model uncertainty. The kind of baseline approaches is just the kind of simple model exclusion where models are thrown out based on their agreement with observations. Then there are kind of fancier recalibration methods where those biases are linked to biases in temperature or greenhouse gas forcing or wind circulation. Then there's kind of like model retuning, which I guess is the approach in Jen's recent paper where you kind of rerun a model to try and improve correspondence with observations, and then kind of like in between versions of all of these two, like model weighting. But a lot of these approaches depend heavily on kind of the goal of the assessment or calibration method. Our project is a little bit more focused on that top one, model exclusion, and how we can better utilize some of the more fancy observations we have to do that. A lot of the approaches that I show here have relied very much on the passive microwave sea ice area record to do these things. So next slide. So we're interested in kind of utilizing new observations to assess and potentially improve model projections. Specifically from ISAT-2, I'm very much biased. I've worked on ISAT-2 since it launched in 2018, and it's a great mission providing great sea ice data. And so I've been keen to think about ways we can better use that to assess models. There's a lot of pros to ISAT-2. It's just an incredibly well-performing sensor, giving us really crucial information about that third dimension of sea ice. It's a laser altimeter, so it measures height, and from height we can provide this very accurate measurement of freeboard. It's a measurement of total freeboard, shown on the left here, the difference between the upper snow surface and local sea surface. And those observations are extremely precise, and we have great coverage across both hemispheres. Typically, we then convert that estimate of freeboard to or that measurement of freeboard to an estimate of thickness, and that's where we generally introduce a lot of additional uncertainty related to uncertainty in snow loading and ice density. So additionally, our project is quite interested in this idea of whether we could actually more directly compare the observation of freeboard with a kind of a simulated estimate of freeboard in the models. Obviously, the caveat is that the models don't simulate freeboard, they simulate an ice thickness distribution. So we have to kind of do the opposite of what we might do in the observations and infer freeboard from the provided variables. Sea ice in these global climate models isn't embedded in the ocean, obviously, it's kind of levitating, but we can kind of just pretend for all intents and purposes that it's acting a bit like freeboard in the observations. There's a bunch of cons associated with doing this kind of assessment. It's a very short time period. That's maybe the biggest one that is going to generate probably the most feedback from you all and our potential reviewers. But our hope is that we can maybe characterize what that internal variability is. And yeah, there's some other things to think about in terms of coverage and uncertainty and the uncertainties. Next slide. This is what the data looks like that we're using to do these assessments. So as I said, a lot of the previous work to date has utilized sea ice area observations, which is shown at the bottom row of each hemisphere on these maps. We're interested in these 3 time periods, annual means on the left, and then March and September in the middle and right, broadly representing the peak and trough of the seasonal cycle. And then the ISAT-2 observations are shown in the top 2 rows for the Arctic and the top row on the right for the Southern Ocean. We have freeboard at the top, and then for the winter Arctic, we're a bit more confident about snow loading estimates from accumulation models, and we can, as I said, infer an estimate of thickness from those measurements of freeboard. Chris did some really nice work to kind of think about kind of coverage and how confident we are on the observations, which you can kind of see with the hatchings. So hatchings indicate areas where we have observations from ISAT2, but not consistently every year. So we discard them from our analysis. Next slide. So as I said, we're kind of interested in this idea of directly comparing freeboard. That led us down quite a lengthy rabbit hole regarding freeboard and bulk ice density, which I'll hopefully explain very briefly here. This is explained a lot more in detail in the paper. Thankfully, a bunch of the CMIP6 models provide direct output of ice freeboard. So we can directly compare those to ISAT2 by just simply adding on the snow thickness to those outputs of ice freeboard. How the modeling groups calculated ice freeboard was a little bit confusing to us and unclear. It wasn't particularly documented. So we wanted to dig into that a little bit more. One of the key variables in that conversion is the bulk ice density. So one of the things we did was try and just infer the bulk ice density from the provided variables of ice freeboard and thickness and snow thickness, just to see what that looked like and if that was kind of making sense. That was what kind of initiated this rabbit hole. We also then realized we could calculate bulk ice density in a different way from the provided outputs of mass and volume, which we did as well. Next slide. This is what those results look like, which was kind of interesting. So we're showing now the derived sea ice bulk density from the, I think, 15 or so models that provided the ice freeboard we needed to calculate it using that hydrostatic equilibrium method. Those method 1 results are shown by the different colors and circles. And then those method 2 results using the mass and volume are shown by the black triangles. So for some of these models, it's just a pretty simple case that the bulk ice density is prescribed to a similar value as the remote sensing value of normally around 916 or so. And both methods give the same results, but especially for some of the models with more sophisticated sea ice, we tended to see a difference between those methods, which was a little concerning. So in speaking with Dave Bailey and others, it seems like what's happening is maybe there are kind of different assumptions and different variables used for different purposes. So there's maybe an internal variable, salinity and temperature based bulk ice density, which is used internal to the sea ice model. But then maybe the salinity or density used to provide information to other components of the climate model are a bit different, which is causing some slight discrepancies. Anyway, there's a lot more digging to be done here. Our approach is to kind of ignore all of this and say, okay, what about we just take a fixed ice density value and just calculate ice freeboard and thus total freeboard ourselves, which is what we then do for the preceding analysis. We use this value of 916, which is the same as what we use for the ISAT2 observations when we convert from freeboard to thickness. Next slide. So as I said, we're interested in trying to use all these different observations to assess plausibility, really. We use these 2 different indices. So the plausible range, which is used in those exclusion studies that I mentioned earlier. Then we also have this plausibility index, which is similar to that range, but it's weighted based on the kind of the bias between the model and the observations. I think that should be a negative there, and the direction of that bias too. The key inputs to this are the internal variability, which I said is something we really want to think about, and also the observational uncertainty. Next slide. So yeah, this is surprisingly hard to decide what to do, the observational uncertainty. For sea ice area, the approach often taken is to look at inter-product spread. The downside of doing that is that we just don't have that many products. There's maybe 3 or 4 out there. So our approach was to just maybe go even simpler and just take some guesses, educated guesses, heuristic estimates, if you will, based on various literature views. And this is our kind of summary of what we think the state is, of kind of basin scale sea ice uncertainties from those observations. We have this approach of coming up with a low uncertainty estimate and a high uncertainty estimate, and we try and play around with the sensitivity of our plausibility indices to those values. We assume these are kind of correlated biases, so we can apply maybe the same kind of estimates when we do regional assessments too. Next slide. For internal variability, we again kind of follow what other studies have done in the past. We look at models with at least 5 ensemble members and use those to try and estimate internal variability. estimates for total freeboard are shown in this plot here, but we do it for all the different metrics. We can see all the different models along the x-axis and the CMIP6 mean on the right. We have this just single kind of ISAT2 period 7-year chunk to calculate that, which is shown by the black lines. And then to try and increase our sampling and avoid some of the kind of sampling biases, we also extend our window and do 6/7-year chunks across a kind of 30-year time period that we hope is still climatically representative of that ISAT2 period. We do this similarly for regional scale too, and that's where things get a little bit more questionable based on the ability of models to capture internal variability at those smaller scales. Next slide. This is kind of what our results look like. We have a lot of plots that look like this, where we have essentially the plausibility of those models compared to observations. So we have the observations at the top and in the red line. So it's the Arctic Ocean annual mean freeboard in this case, so around 27 centimeters. We then have the CMIP6 mean below that, and then all the different CMIP6 models ranked based on their plausibility below that. The solid bar is showing the plausible range based on the low uncertainty estimate, and then the whiskers show it with the high uncertainty estimate. So for the Arctic, a lot of these models are performing extremely well, which a lot of you know already. This is a bit different because we're showing freeboard instead of area. But again, the CMIP6 mean is incredibly close to observations. And just a few of those models at the bottom there are showing results that we would maybe consider implausible. We're using 2 sigma here, so it's kind of a 95% confidence level. Next slide. Things get a bit more dicey for the Southern Ocean, which again is following on from other studies that have shown this for area. So we see a much clearer bias between CMIP6 and the observations, and a lot of models that are considered implausible, even if we use that more relaxed uncertainty estimate. Next slide. As I said, we had lots of plots that look like that. So we tried to then bring this all together into one consistent figure. So we're now showing all the different metrics across both hemispheres for those 3 time periods in each subcolumn. The models are ranked based on their plausibility, averaged across all of these 15 metrics. We have CMIP6 at the top, which we put there at the top, but actually is one of the better performing compared to all the individual models. Luckily for this group, CSM2 is one of the better performing ones. Yeah, really doing quite well across both hemispheres, which again has been kind of highlighted in some of the talks already during this meeting. There's maybe some evidence of that kind of low bias that people have talked about in Jen K's study, that kind of end of summer low bias. But again, it doesn't seem as significant as some of the other models. So it would be interesting to bring in that CSM2 less melt output into this as well. Access ESM1, the only one that seems, according to our thresholds, plausible across all of these metrics and hemispheres. Next slide, please. So then we're kind of interested in thinking about what that does to projections. Our goal is a little bit more focused on kind of highlighting how to use the observations and kind of those questions about uncertainties and internal variability. But here are some results on the left showing the impact on the seasonal sea ice volume, constraining it based on just area and then based on all of those metrics. So we don't see a huge difference for the Arctic on the top, but we see much bigger shifts in the seasonal cycle for the Southern Ocean at the bottom. And then we also looked at kind of the impact on things like the future ice-free Arctic projections, and unsurprisingly, big shifts there based on the constraints that we apply. Next slide. I think I'm probably running out of time, or already gone over. We've also looked at regional sea ice assessments. Again, this gets maybe a bit more shaky based on how much we trust the internal variability estimates. The map's shown at the bottom right there. The hatched regions now indicate areas that we consider implausible based on a combination of that regional internal variability and the observational uncertainty. So a lot of those well-performing models still struggle to capture some of that thick ice north of Greenland and Canada, for example. There's a lot more regional assessments, but I would encourage you to check out the paper if you're interested in that. So next slide, we'll just finish with some discussion points. Yeah, bulk ice density became a rabbit hole, but a kind of interesting one. I think we need to think a little bit more about how density is simulated in models and the kind of values that we should expect that to look like. especially if you want to compare freeboards. We need better uncertainty quantification. We took a very simple approach. Things like observational ensembles would help us better constrain that. Internal variability estimates, obviously are one of the big caveats and questions of all of this kind of work. And we're hoping to kind of build on what we've done and maybe combine some of this work of exclusion or plausibility with some of the existing recalibration methods. And then, yeah, I'll finish with this final slide, next slide, which is just some of the next steps we hope to take in the final years of our project. Thanks very much.
Marika?
Yeah, thanks for a very nice talk. So we're in the process of developing CESM 3. And so I guess I'm wondering whether you're thinking at all about using this in the model development process, or if you would be willing to collaborate with us to use it in, developing this model. And we're trying to assess the model. A lot of what we're doing is based on ice concentration and, the passive microwave record. This would be really nice to bring in as well.
Yeah, I mean, that would be great. I think we've really wanted to do that, and we really want to kind of work with the community. I'm a little bit involved with SIMIP. I've been a bit, I don't know, wary of there's a lot of toolkits that are out there, and we didn't want to produce another toolkit, compete with other toolkits, and I'm not quite sure on the best approach there. As you say, whether it's best just to kind of partner up and deal with things more ad hoc versus putting something out there for people to use as they want. So yeah, very much trying to figure that out, but would love to help with CMIP and CSM3 developments for sure.
Yeah, maybe we'll reach out after the meeting.
Yeah, great. Thank you.
Discussion at the end of the morning too about kind of CESM 3 developments and potentially coordinating manuscripts or who wants to.
Yeah, awesome.
One more quick question, David?
Yeah, Alec, nice talk. And I was wondering if you've thought much about uncertainties in snow density, and particularly snow on Antarctic sea ice. I've never worked down there, but Rushla has given some great presentations on, the snow that basically looks like concrete in its microstructure.
Yeah, I try and avoid commenting on that. Yeah, that seems like another whole rabbit hole that I'm sure we'll eventually have to go down. But yeah, snow density is, it's hard. And kind of one of the big reasons why I think we're pretty resistant to generate sea ice thickness estimates in the Southern Ocean too.
All right. Thank you, Alec. We're going to move on to our next speaker, which is Melinda Webster.
Okay, great. Well, David, thanks for the snow question. That really helps us get thinking about snow on sea ice. And so for this talk, I'm going to present some results from observations and a Lagrangian single column model. And then I'm going to end with some questions for the climate modeling community. So no conclusions. So to kick things off, let's think about Arctic sea ice. And one of its key superpowers is its high albedo. The Arctic sea ice is a very heterogeneous medium. So depending on where you are in the Arctic and what time of year you're there, you can get an albedo of 0.13, 0.15, or an albedo of 0.85. If you wanted to look at what type of surface is most dominant in space and time on Arctic sea ice, it's the snow on top of the sea ice. And it's really interesting because this is also the most reflective type of surface condition for Arctic sea ice. It doesn't matter if it's really thick or if it's really thin. It doesn't matter if it's wet snow or dry snow. It's all about the albedo of the snow on top of the ice that dominates this albedo for Arctic sea ice in the spring and sometimes into the summer. So it's interesting to think about where snow is, what time of year it's there, and how much is there. And I like thinking about this, or I think it's a really fun way to think about this in the context of summer, when a little bit of snow goes a very long way in increasing the surface albedo. To give you some context for this, you just need maybe half a centimeter of cold, dry snow to boost the albedo to reflecting nearly 80%. Or if it's really coarse grained stuff, you need about 2 centimeters. So a little bit goes a long way. Now, how do we get a snowy summer? There are, I guess, 2 simple ways to think about this is how much snow is left over from the winter time, from what's accumulated during the autumn, winter, and spring. And then how much is new snow accumulation? And so this is a problem that several colleagues and I were interested in exploring, and it was a lot of fun digging into some of the old historical observations to figure out, well, are snowy summers an important thing or not? So first off, is it snowing in summer? And if you dig into the historical data, there's a big yes. They had very snowy summers during the North Pole drifting ice stations. They really enjoyed it when the summers were snowy. They really didn't like melt ponds. So I thought that was a really interesting context for snow on sea ice. But what about the contemporary period? So this is from like 1930s, 1950s, 60s, 70s. What about more recent times? And well, we're getting an idea that it is pretty snowy still during the summertime. And Mosaic is a really nice example because it was unusually warm. This was a year-long drift experiment, and the summertime was in 2020, so a very cloudy and warm summer, but there were still about 15% of the snow persisted, and it really hung out in these large drifts. So in the snow drifts by ridges like this. But what about new snow accumulation? So that's the case for leftover snow from the winter time. My student did a really nice job in digging through a lot of ice mass balance buoy data and quantifying how many snow accumulation events occurred in the summertime. And so she counted this from initially snow-free conditions. So really counting what the albedo effect would be based on new snow accumulation from snow-free ice. And on average, so this is from 2002 to 2020, on average, there's about 2 to 3 new snow accumulation events that happen per year. And it's very small amounts, 2 centimeters, but like I mentioned before, that's enough to raise the albedo quite a bit. And they didn't last very long, but we still looked at this in the perspective of radiative forcing. Was it important? Did it make a difference? And so using a very simple radiative transfer model, she found that it did decrease the top of the atmosphere radiative forcing by 0.09. So maybe it's important. It gave us motivation to dig into this relationship between snow and summertime sea ice a bit more. And I was really interested in this, seeing how frequently summer snowfall happens. I wanted to know, well, what drives that? Is this natural climate variability that snow can respond to, or is this just noise? So that's really what helped direct this next line of work, which is done with quite a few people. So this is thinking about the Arctic oscillation, and granted, I'm not an atmospheric scientist, but I can tell you with certainty the snow on the ground comes from snowflakes developed in the atmosphere, or produced in the atmosphere. And precipitation, especially snowfall patterns, is strongly affected by the Arctic oscillation. It's the leading mode of climate variability in the Arctic. So for this, I was really quite interested in the positive phase of the Arctic oscillation, where you have a very strong jet stream, and it allows cyclones, which are an important mechanism for establishing snow on sea ice. It allows these cyclones to penetrate deeper into the Arctic. And so I was wondering, well, if it's affecting precipitation, temperature, snowfall, shouldn't it then also affect the snow? So that's what we wanted to dig into. So our tools for looking at this is a snow model LG. This is a Lagrangian process snow model developed by Glenn Liston and several others. And it has a whole slew of processes that it represents. But the one that we were most interested in is melt, because we're looking at summertime snow. We also looked at several other things like Era 5 for the atmospheric state, satellite albedo, melt and freeze onset, ice concentration, and we threw in data observations where we could. So this is a pretty complex analysis, and I'm going to gloss over a lot of details, so feel free to ask questions during the break if you want to learn more. Now, our first line of action was to see if there was even a relationship between snow on sea ice in summertime and the Arctic oscillation. And for this, we're using a number of statistical methods. We're looking at the snow depth anomalies for June, July, August. We did this on a monthly basis, but for clarity, I'm just showing the 3-month average here. So we looked at the correlations with the AO. We regressed the anomalies onto the AO. We also performed a composite analysis looking at the extreme 5 years of positive AO and the extreme negative AO summers. And then we also looked at the first principal component. And they all show the same result, that there is a strong relationship between the presence of snow in summer and a positive AO index during the summertime. And to give you an idea of what this would look like, it's about 4 to 5 centimeters of snow near the North Pole or in the region of the Central Arctic, which is certainly enough to increase the albedo. When we looked at the satellite retrievals of albedo, we saw that they increased by 0.1, which is not nothing. That's really nice for the sea ice, especially during the peak insolation period of the year. But that doesn't really get at the question of whether this is snow that's left over from the wintertime or if it's new snow during the summer. But for this, we looked at monthly lagged snow depth anomalies, and I'm going to skip the top panel. So if you have questions about that, we can talk during the break. But on this bottom panel, so these are the monthly correlations between May and June, May and July, and May and August. And the key thing is, it's really important what happened in the wintertime for June snow depth variance. But after that, it doesn't really matter. It's like that memory is lost. So this is also really important thinking that in June, that's when we have the most sunlight hitting this surface of Arctic sea ice, or the snow on top of Arctic sea ice. So knowing how much snow there is really important. And the spring measurements that we can get from satellites can really help us understand how long that snow may persist. Now for July and August, it's really about what's happening in the atmosphere. This is a little messy, so you'll have to be patient with me as I walk through this. I want to show, I didn't want to show a million postage stamps of maps, so I'm just showing the correlations between these variables and the AO, which is why there are 4 panel Bs. But for positive summers with the AO, there are more storms, more cyclones, and penetrating deeper into the Central Arctic. And not only that, they're stronger. And then the third ingredient for snowfall is there are cooler temperatures aloft. And so not only are we having more precipitation during these positive AO summers, they're coming in, that precipitation is coming in the form of snow. So I think that's a really neat result in demonstrating that there's more frequent snowfall and heavier snowfall during these positive AO summers. We did look at the surface temperatures, and even though it shows that there's a relationship here, it was not statistically significant. So I can't say with confidence that that snow is persisting because it's colder. But maybe that's also has something to do with the biases in ERA 5, since snow isn't truly represented in that model. So that's a line for future work, perhaps. So this is a really exciting study to me, because we established that there's this relationship between snow on sea ice in the summertime and the Arctic Oscillation. But what was weird is that this relationship breaks down in 2007. And there's no trend in the summertime AO. There is a trend in the wintertime, but the summertime there isn't. So we weren't really sure why this relationship breaks down. Maybe it's because it's simply too warm in the summertime, so you have less snowfall. There are studies that show that there an increasing trend in pressure in the Arctic, so maybe it's sunnier, I don't know. Or maybe it's just so warm that the snow can't last as long when it does accumulate. And then there's also less ice area to capture the falling snow. So this is a question, or this has inspired me to ask a lot of questions to the climate modeling community that would be really fun to dig into, especially if anyone's interested in these problems. I'd love to collaborate. So the first question is, well, how persistent is the spring snow on Arctic sea ice in the models? What we've seen from historical data and from contemporary data is most of the snow is gone by mid-July, which seems like that would be an important thing to get right in climate modeling, since you have peak insolation in June. But there can be snowy summers, so it'd be helpful to know how often and how much new snow accumulation there is in July and August. We have some baseline metrics from the little observations that we have, but I think this also motivates getting some meaningful answers from fully coupled climate model experiments, and that is, are these summer snowfall events important at all? What sort of radiative forcing effect does summer snow have, and can models help us disentangle some of these processes to get at that answer? Now, switching gears a bit, my next question has to do with natural climate variability. So I think maybe incorrectly that if we want to understand how snow responds to climate change, it might be helpful to understand how snow responds to natural climate variability. So do models capture this relationship between the Arctic oscillation and the summertime conditions? And also, do the models show that it's really about what's leftover snow from the wintertime, or what's new snow accumulation related to what's happening in the atmosphere with cyclone patterns and such? And then also, do climate models show that this relationship breaks down over time? I don't know, and I don't know why it's breaking down in our observations. So maybe there can be more insight there from fully coupled model experiments. So with that, I will stop and thank you for your attention, and I'm happy to answer any questions.
Questions in the room? Will?
Yeah, thanks for that. Really nice talk. I was curious about this what you're saying about the relationship breaking down. My knowledge is kind of shaky on this area, like the AO and thinking about different times of year. I remember reading about something about how the AO kind of transitioning into more of a negative phase, roughly around that time, 2000 something, a bit earlier. Could that be something that's going on here, where you're in a, because you were saying it's a positive AO phase that kind of correlates with these snow events in summer? Is there something to that? Or?
Yeah, we wondered about that. And that's certainly a thing that's happening in the wintertime, but we didn't see that sort of long-term change in the AO indices for the summertime period. But, you know, thinking about this a little more, maybe that has something to do with that remnant snow. Maybe it's just not sticking around as long, or maybe it's thinner. So there could be a piece of that wintertime AO trend being imprinted on the summertime relationship that we're seeing. That's a good point. Thanks.
Yeah, thank you for the talk, especially the questions. I'm wondering what snow data did you use in your analysis about AO and snow?
Yeah, so the key data set that we used was from the snow model LG from Glenn Liston and others for the monthly anomalies and things like that. And to validate the model, we did an analysis, and we used the historical data from the North Pole drifting ice stations. We used data that were from in-situ surveys from all sorts of field campaigns, and we also used the ice mass balance buoys. So it's a conglomeration of different data sets from different periods, from 1950s to, I believe, 2017.
They provided depths.
Yeah, they provide the depths. There's also density data for some of them as well.
All right. Thank you. Oh, sorry. Go ahead, Dave.
If it's okay. They're wonderful talk as always. I'm kind of curious about this question of the role of the snowfall in this. And if there is snowfall in summer, you know, we know we get it in the model, but you know, do we have good observations of like snowfall events during the summer? Is there a way that we can assess that?
Yeah, there's a few. And actually, I started digging into this as a graduate student when I came to visit, right? So we have the buoy data, we have stuff from field campaigns, and I think it would be really nice to connect that more closely to albedo measurements too during those events to see if the model can get that right.
Yeah.
Those are very sparse, but they do exist.
Yeah.
That could be something we work on this month.
Next month. Yep.
All right. Thank you so much, Melinda. Our next speaker is Elizabeth Hunke to talk to us about snow, but in the model virtual world.
Okay, so this is an update on the last talk I gave for Polar Climate Working Group, which was also on the snow physics, and I think it was in 2015. It's it's been a while. This is a project that Nicole Jeffrey and I have been working on off and on for many years, more off than on. But to cut off some of your questions right at the beginning, there's a whole lot more that we need to do because we haven't spent very much time on this. So some of the things that I'm going to be talking about the sea ice, of course, but some of the things that we need to do is look more closely at the analysis or analyze the output from the atmosphere and the ocean model. We need to look at the full historical ensemble that has been run and put this in the context of that. We need to look at observations and do more parameter sensitivities than I've already done. I've done a little bit. So this work is with E3SM, the Energy Exascale Earth System Model, which is DOE's climate model, and it branched from CESM about a decade ago, about the time that we started this project. There's two main parameterizations in what I call the new advanced snow physics. There's snow redistribution by wind and snow grain metamorphism. And in my slides, I say metamorphism, but I refer to the runs as grain. So those two go together. The snow redistribution includes snow compaction by the wind. Snow can be lost to leads or open water, just disappears from the sea ice. And there is an interaction with ridges where the snow, some of the snow can be blown from the level ice and pile up on the ridges like Melinda was mentioning. For the snow grain metamorphism, here the snow grain size evolves as a function of both wet and dry processes, and this is based on the land model in CESM. And then for both of these, since you're changing the snow, the main interaction with the sea ice and the rest of the climate system is through radiation and albedo. But for snow redistribution, we're also actually losing snow off of the ice, so that has an impact too. There are 4 sets of simulations that I'll talk about listed on the left. G+R has both of those sets of parameterizations run together. And then I did runs with just redistribution on without the metamorphism, and then the opposite. And then also runs where all of the advanced snow physics is turned off. But of course, we still have basic snow thermodynamics. And then over on the configurations column way over there, I can look at the effects of coupled feedbacks by considering the historical runs, which are fully coupled cases, 1850 to 2014. I'll be showing you the last 30 years of that. I've also done CI standalone runs. These are only 5 years old, 5 years long, but it's sea ice in a slab ocean. This is our standard quality control tests from the SICE consortium. And then I've also done some runs in IcePack as a column model. Okay, so a lot of what's happening in the simulation can be understood in terms of the physical principles that we know, that we already understand. So first of all, snow is an insulator, and so if you have more snow, it's gonna increase the growth and melt. And so it stands to reason if you throw the snow off into the ocean, the ice growth and melt may increase. Of course, that also reduces the albedo. But the snow albedo effects from both redistribution and the snow grain size are really only active in the summer months when there's light. And then there's several ways to get rid of snow. In the redistribution, we are throwing it off, but we can also convert snow to ice through snow ice formation. The basic ridging parameterization has thrown snow into the ocean right from Bill and Cece's graduate school days. That's been in the model forever. But then the other thing to think about is that ridging is a volume conserving process for the ice, but for the snow, it throws it off. But as it's conserving that volume, it's converging. And so that tends to open up some open water area. And so if you have ridging, then you often also have enhanced thermodynamic growth and ice thickening when it's freezing because of that process. So those are kind of the outline of the processes that I'll be looking at here. To illustrate some of them, I'll show you first some runs from IcePack. So this is just column physics. These are 10-year runs. And if you start over there on the right, the run with none of the advanced snow physics on, at the bottom is the snow depth, and you don't have any redistribution or metamorphism. So, you know, there's your snow depth. Use that as a baseline. Take one step to the left. In the run where only the redistribution is turned on, you lose the snow, you have a lower snow depth. Okay, that's understandable. Another step to the left. This is the run with just the metamorphism without redistribution. And so you don't lose the snow initially, and we see that the snow gradually increases over time in IcePack. And that, because of that, the ice volume grows quite a lot in IcePack. And if you look at the seasonal cycle there in those little lumps and compare that to, say, the off run, it appears to be because the metamorphism is reducing the ability of ice to thin in the spring. And this is where I've done some sensitivity studies, again, with IcePack, and I think Dave already did this, maybe you too, that the critical parameter here is the snow grain radius for freshly fallen snow. So not surprising, right? Okay, so then another step to the left, and you see with all of the advanced snow physics on, you have some initial loss of snow at the beginning of run because of the redistribution, then it begins to grow very gradually. So that's the, you know, here's what's going on in the column physics, but I want to go beyond that. And I have to apologize to Melinda. I'm not going to show any results for the Northern Hemisphere. I looked at the Northern Hemisphere and there's a lot of stuff going on up there, but the most interesting part was in the Southern Hemisphere. So that's what I'm going to show today because I only have a little bit of time to talk. So the top row here is with both on metamorphism and redistribution. This is ice thickness at the end of the run, the last 30 years, and I'm comparing with all the advanced snow physics on the left with none in the middle column, and then the difference on the right. And so what was so interesting to me was that we had this spatial pattern where in the wet LC, the ice got thicker, and on the other side of the Antarctic Peninsula in the Ross Sea, it got thinner. And that signal, I think, shows up a lot because of the southern annular mode, or, you know, that's not unusual. But in this comparison, that is coming solely from the snow physics. Okay, so I have these other runs. We can compare just the metamorphism versus off, and we see that metamorphism tends to thicken the ice everywhere. Same likewise for just redistribution by itself, it tends to thin the ice in those areas that we're interested in up there. Okay, so it looks like metamorphism drives the thickness changes in wet LC, and redistribution drives them on the other side. But it's more complicated than that, of course. You know, this is the Earth system. What we see here now, comparing a run with all of the advanced snow physics on with one where only the redistribution is on, what you're looking at is the effect of metamorphism in the presence of redistribution. Okay, and so what you see in that case is that in the wet LC, the relative thickness of the ice, it's even thicker when you have redistribution, which would normally thin the ice, right? So this is a little counterintuitive. And likewise, for redistribution in the presence of metamorphism, the ice in the wet LC gets thicker. That's not too surprising because of the snow grain radius thing. It really thickens the ice. But on the other side, it gets even thinner. So this was interesting to me. And so since I'm not looking at all the atmosphere and the ocean and the ensemble and all that kind of stuff, I just dug in on the snow processes themselves. So to see if I could understand this from a mechanistic point of view. And so here's some examples. Other processes that we have in the model are like snow ice formation. That's converting snow to ice. And so it tends to thin the snow. And therefore, that process itself would tend to enhance the effect of the redistribution physics in the model, which also tends to thin the snow. Okay, and then it has the opposite effect for metamorphism, where the snow tends to get thicker, the snow ice formation would tend to counter that. Likewise, for snow loss during ridging, it does the same kind of thing. Then, as I mentioned, for redistribution, we also have albedo changes on the ice due to the snow being, some of the snow being moved from level ice to the deformed ice. And what that does depends on how much level and ridged ice you have. And in general, it's less important than actually losing the snow completely off into the ocean. That's going to always be a bigger effect. But these last two give you a hint that ridging might actually be important here. Okay. So let's look at some of these processes a little bit more closely. This is the snow ice formation rate. And I'm showing again these same combinations of differences of runs. So the ones on the left, the two on the left are the effect of redistribution without metamorphism and with it. The two on the right are the effect of metamorphism without redistribution and with it. And then the one in the middle is all the advanced physics versus none. Okay. So what we see with the snow ice formation rate is that it looks like it is actually enhancing those spatial differences with thicker, with a greater snow ice formation rate in the wet LC and smaller on the other side. So that could be contributing here. For metamorphism, it counters that. Okay, there's blue, there's less in the wet LC and more on the other side. And so that's consistent with what we said up here with snow ice formation. It's doing what we might expect. But now, if we look at the ridged ice thickness, same plots. Look at number 3 here on the left. Redistribution tends to reduce the ridged ice everywhere. Okay, go over there to the right. Metamorphism increases it everywhere in isolation. But if you come back here to the effect of redistribution in the presence of metamorphism, then you see this pattern, and it really sticks out. You know, it looks like to me that ridging is actually enhancing this contrast that we see in the ice thickness in this case. Okay, so that's all sea ice snow processes. And so I did step back a little bit and look at the standalone sea ice runs to see what effect coupling might be having in here. And there's a lot of plots here. I'm not going to talk about each one. The point is the plots on the left are September, October, November. It's similar for June, July, August. The ones on the right are December, January, February. These are all different kinds of output variables from the model that are appropriate to look at in those seasons. And what you see looking across is that they're very similar for redistribution by itself or redistribution in the presence of grain, or likewise metamorphism or more metamorphism in the presence of redistribution. They're very similar across those. So this interaction that we see between metamorphism and redistribution is coming in through coupled processes. I think there's a caveat here. This is only a 5-year run, but you know, that looks pretty clear to me, except for the ridging. Okay, that's the one that's different. All right, so I don't really know what's going on, but I do have an idea and something that I want to look into more closely when I get back to New Mexico. And that is an interaction between the katabatic winds and the movement of the ice in the Antarctic coastal current. So the katabatic winds are pushing the ice away from the coast. They tend to open up plinias, as was mentioned yesterday. Meanwhile, the ice in the Antarctic coastal current is going counterclockwise around the continent. The Coriolis would tend to turn that toward the continent, okay? And so that would tend to make the ice converge toward the continent, make it ridge more. But they're both processes increase ice production because, you know, ridging allows some open water formation. So you get additional production there. And then what we're looking at in all these simulations is the snow processes. And it's quite conceivable that the snow processes would modify those things and vice versa. Okay, so that's my idea. That's what I want to look for. And so this is my summary slide that, first of all, the coastal dynamics in the Southern Hemisphere appear to be really, really interesting. There are strong spatial differences, they're nonlinear, they're coupled, and they're counterintuitive because the metamorphism and the redistribution enhance each other rather than canceling each other out as we would expect based on the ice pack. Okay, there's a lot more work to be done. I already said that. The hypotheses that I have going forward are, first of all, that the thermodynamic feedbacks associated with ice production, not necessarily only snow ice formation, but also, frazzle ice formation, that kind of thing, that those changes are setting the stage, and then ridging is amplifying the differences near the coast over time. And what's setting up the overall pattern that allows this is this balance between the large-scale pressure systems, katabatic winds, and the coastal current. And so that's my talk.
All right, I think we have time for a question or two. David?
Oh, David?
No, Dave.
I would actually ask questions.
Anyway, that's nice. I think we saw similar sort of results in our coupled runs. But I guess there are sort of three things in the snow physics. You didn't really mention the liquid from snow melt in this. You talked about the snow grain evolution.
Yeah.
Was that included in your runs?
Yes.
Yeah, okay.
Yes, it
Okay.
was. And I did look at albedo. I looked at a whole bunch of fields, and the patterns generally follow these. So this is what I showed you, but yeah, I did look at all that. It didn't seem any more significant, probably, than what I showed you here.
All right, one more question. Online in the room. Melinda?
I'm in your also, thank you for the really nice presentation. This is fantastic. I noticed in your text that you mentioned melt ponds. Was that solely for the Arctic, or did you see melt ponds in the Antarctic?
We have the ability to have melt ponds in the Antarctic because this is partly what Dave is referring to. The meltwater infiltrates the snow, and then when the snow gets thin enough, the melt ponds become visible. But we have that meltwater there.
Okay,
And so we do see them sometimes.
cool.
Yeah.
All right, thank you so much, Elizabeth. Last but not least, to talk about melt ponds, we have David Clemens Sewell. Sorry that we're a little bit behind, but I'm glad we're having some good conversations here too.
We wrote them.
Okay, thank you everyone for being here. I'm sorry that I am already keeping you from your scheduled break. And I will endeavor to not go too badly over into the break. My name is David Clemens Sewell. I would like to stress that I am presenting this work in my personal capacity as a private citizen. This work was funded thanks to the National Science Foundation and to NOAA's Global Ocean Monitoring and Observing Program. And before I jump into the science, I want to take a really quick appreciation to all of my co-authors, but especially to Dave Bailey, who, this is going to be a talk mostly about science because I think it's more exciting for most of you if we talk about melt pond physics rather than debugging bit for bit comparisons in SAIS and such things. But the goal of this work is to make improvements in SAIS. And that would not be possible without all of the work that Dave does, and that rarely makes it into
posters and talks and all that stuff. So, thank you, Dave. Okay, so to motivate this, we've heard a lot about how important albedo is for the sea ice. And so the plot up here on the screen is showing a comparison of the summertime albedo evolution simulated by CSM2 and shown and observed on a couple of field campaigns, Mosaic and Sheba. And I won't bother discriminating the lines for you because they are overlapping. CSM2 simulates an excellent summertime albedo evolution. And so great, why am I still here talking to you about this? The surprising thing is that maybe it shouldn't simulate such a good albedo evolution. And so the upper leftmost plot here is now taking this albedo just for the middle of the summer and breaking it out by category. You can see that the snow albedo aligns great between CSM2 and observations. The bare ice albedo aligns great between CSM2 and observations. And the ponded ice albedo is roughly double CSM2 relative to observations. And coincidentally, if we compare the ponded ice fractions observed on the campaigns and in the CSM2 simulations, the ponded ice fraction is about double in CSM2 relative to the observations. So we have offsetting errors here, and they just happen to align such that we get this beautiful albedo evolution. Well, if we mostly care about the albedo evolution, why do we care? Why is this a big deal? And oh, we had some funny PowerPoint to Google Slides transitions here. So I have three first points I'd like to make. Number one, we have no guarantee that these errors are going to continue offsetting in different sea ice states, right? We need to run climate models in all kinds of different states. We want to predict the future, not just the past. There's no guarantee of that offsetting. Second, the errors limit our ability to improve model realism. And so if we think about, melt pond fraction in the summer is one of the better satellite observables of the sea ice state. If we wanted to assimilate that into a model, well, we couldn't do that in the current configuration because it would degrade our albedo evolution. And then finally, albedo isn't the whole story. So you can get the right albedo evolution and the wrong light transmission, and that's going to impact both the solar heating of the mixed layer and light available for sea ice algae and other phytoplankton. So the remainder of this talk, I've already provided you a motivation. I'm going to talk a bit about the life cycle of a melt pond on Arctic sea ice, because this is, I think, where I think the key insights for updating these parameterizations come from. First of all, what is a melt pond? Melt pond's a puddle. It's a puddle that accumulates on the surface of sea ice, similar to how puddles accumulate basically anywhere else in the world that you're used to. The photo on the left here is showing Zach Espinoza making a spectral albedo measurement in a melt pond. And on the left side, you can see satellite imagery of melt ponds, which we can use to derive melt pond fraction. So we often look at melt ponds from above. They make these beautiful images. But in terms of thinking about how the physics work, how the model works, I think it's useful to look at these from the side. So I'm going to show various cartoons that look like this. But just remember that these cartoons are, one, I'm not a very good artist, and two, where this is just a cross section of this. And we know quite a bit about how melt ponds form and how they behave, and we've known this for a long time. So one of the best references for this comes from Hayo Aiken's work on Sheba, so 20 plus years ago now. And what they did was they identified 4 phases of melt pond evolution. Phase 1 is the first time ponds form. We get meltwater on the surface, it pools in depressions, it begins lowering the albedo,
and it begins driving preferential surface melt in the areas under the ponds that cause the ponds to deepen such that the ice surface sits below freeboard. And this is really critical because in phase 2, the ice becomes sufficiently permeable. We develop sufficiently efficient lateral flow networks to macroscopic drainage holes. And the pond water now drains down to sea level, more or less. And from there, the pond level essentially stays at sea level throughout the rest of the summer because the water is fully connected to the ocean. And it stays there until, that's stage 3. And it stays there until stage 4, which is the ponds refreeze or the ice completely disintegrates. And if you have melted through the ice underneath, you no longer have a pond, you have open water. Maybe in the shape of a pond, perhaps. And what has changed since Eichen and others did their work on Sheba is our ability to observe these from space has improved dramatically. And so we now have, there's various platforms to do this. I'm only going to talk about high resolution satellite imagery. This was collected by Nick Wright and Chris Polashensky is in the figure here, but it's also been collected by Melinda and many other folks to observe this. And so this plot in the bottom left here is showing melt pond fraction from I think over 1,000 images of sea ice taken during one summer. And the x-axis here is the time since melt onset. So the time since ponds became observable at the surface from satellites. And one of the things you'll notice is it has this same characteristic shape that was described by Eichen et al. 20 years ago, where first in stage 1, the pond fractions shoot up. The pond fractions can be highly variable in stage 1 because it depends on the particulars of ice topography and the connectivity of different topographic basins on the ice. Then in phase 2, the ponds drain down. And finally in phase 3, the ponds continue to stay within kind of a narrow range of pond fractions. And from a fundamental physics perspective, this is a really interesting curve. From a model development perspective, it has one really nice feature, and that's that ponds spend most of their time in stage 3 of this. And so if your goal is to make an improvement in capturing the pond physics in sea ice, getting it right in stage 3 gets you most of the way there. And stage 3 is nice because there's actually a lot of constraints on the system because it is connected hydraulically to the ocean. And so we see in these observations in stage 3, pond fractions tend to stay between about 15% and 40–45%. That's actually not an accident. So I can see Alice already looking at her time. So I'm gonna go through this quickly. So just to motivate why that might be the case, why that's not just a coincidence that happens, I want you to briefly consider a small rigid piece of sea ice with some variable surface topography on it that is fully connected to the ocean below, such that the height of the water on this, and hence the pond area, is controlled simply by the balance of buoyancy and by the variation in surface topography. The real ice could look something in profile like this over here on the left. For simplicity and because, again, poor artistic skills, I'm going to represent it as this simple trapezoidal shape with the pond demonstrated there. It turns out that in this system, you can actually solve for, given a surface topography variability, so given the height of the slope of this elevation distribution, what should the pond area be due to buoyancy?
And the key point for this is, and that's what's shown here in the bottom left. The key point is that this is a sort of asymptotic function. And the actual observed range in pond fractions during stage 3 kind of fall where you'd expect them to be in this function, right? So if you start with a really low pond fraction, well, ponds drive differential surface melt, so you get a more variable surface topography. That brings you into this sort of range of the curve. However, you know, in order to get to really, really high pond fractions in this model, you need really, really extreme topography variations, and that's not really feasible in the real ice system. And so all of this is to justify that providing using this kind of model to establish what should the pond fraction be in stage 3 of pond formation. It's actually fairly natural to have kind of a target pond fraction when the pond surfaces sit at sea level. And so that's basically what we have implemented in IcePack. In the interest of time, I'm actually not going to talk about the level ice pond parameterization, but I'd be happy to talk about that more, or if, of course, the expert is, is sitting in the room here. But this is what we have proposed doing in IcePack. And so we've proposed that on the per category basis, explicitly representing this elevation distribution. And then using this elevation distribution to compute pond area, pond depth, and to compute drainage. We'll skip over this. And then finally, the only unknown parameter in this is what is the slope of that elevation distribution. Rather than attempting to derive that from first principles and have that evolve prognostically with things like ice ridge fraction, for simplicity, we have actually made this a tunable parameter as a function of ice thickness. So given so in the name list in IcePack, it's now possible to set what should the pond area when the ponds are at the sea level be in a SICE simulation. And so this is just an example of how the hypsometry works for that. All right. I know I also talked about the pond albedo being off. In the interest of time, I'm going to skip over why that is, but please feel free to come talk with me. That has less of a physical explanation and more just a choices made during the implementation of the Delta Eddington code back 20 or so years ago reason. And I originally in this talk, I wasn't planning to talk about IcePack at all, but your presentation yesterday inspired me. So I will show one slide here showing that when we implement this new parameterization in IcePack and compare with standalone mosaic simulations, it does an excellent job of recreating the pond evolution that we actually saw along the ice thickness and pond depth transects that Melinda observed and put together. I'll also highlight before I show any coupled results. Again, at the outset I said our albedo evolution is really good, so we didn't want to screw that up with this parameterization. And remarkably, we've actually done that. So this is showing the SICE QC test. This is a standalone ice model forced by atmosphere and ocean, comparing the difference between the new parameterization and the old level ice pond parameterization. And you don't see much on this plot because at least in standalone runs, they don't produce climate changing differences. So that's good. So that's what we had hoped here. Finally, and I know I am now over my time, we have been doing tests in CESM3, and as often happens when you put things into a coupled model, you get more changes. And so it does appear that this change is, the new parameterization is climate changing, excuse me, in our CESM3 development runs. Oh, we've had another PowerPoint to Google Slides transition here. But what this slide is showing is that at least the July ice area is not particularly different in the top row between these runs, but the ice thickness is actually different. So using the new pond parameterization, we get to less ice thickness, we get less thick ice in the summertime in the Arctic than observed for the level ice parameterization. And also just to bring things back to this question of, well, do you have albedo differences versus transmission differences? I will highlight that in the new parameterization, the albedo changes are relatively small, still significant in the top row here, but the transmission changes are considerably larger. So in the central Arctic, we're seeing roughly double the transmission of light into the ocean mix layer below. So with that, I'm well past my time, but thank you all very much for listening. My hope here is that this parameterization and adding subcategory elevation distributions to IcePack and SEIS is step one in being able to have a more physically realistic prognostic melt pond schemes. Thank you all for listening, and feel free to reach out if you're interested.
All right. There might be one question in the room online. There's a question here. Do you have field observations that show, well, the meltwater ponds get deeper during the melt phase? I would think that the melting would be enhanced along the edges of the pond instead of at the bottom of the ponds, which would make the ponds wider instead of deeper.
Yeah, thank you for the question. I think the short answer is yes to both. And it depends a little bit on the timing in the summer that you're thinking about. So right at the very start of the summer during phase one, the melting does, right, when the ponds are still relatively thin, the melting has the impact of making the ponds deeper, making the ponds deeper under the ponded surfaces. As the ponds get deeper, the balance of ice melt shifts more and more to lateral melt. And so it's sort of an answer to both. The one thing that does change though, as you get to stage 3 of the melt pond evolution, when we are laterally melting out the ponds, we're decreasing the ice thickness as well. And so the ice is free also to isostatically adjust underneath there. And so it can have a slightly unexpected impacts from just the balance of like where the melt is happening and then also how the ice itself can flex and respond. Sorry, hopefully that answers your question.
All right. Thank you, David, and thank you to everyone else who gave presentations this morning. So let's give ourselves 5 extra minutes of the break. That way we get a full 15-minute break. So come back at 10:35 and we're going to have some information about CESM3 and a discussion about manuscripts and stuff like that. So see you online and in the room soon. So good. And so we're trying to figure that out. We'd like feedback from the community and also to discuss what manuscripts we think there might be written throughout the Polar Climate Working Group community so that we can kind of coordinate if need be, or if there's a special issue, we want to be able to inform people about that. But before we start, I just wanted to ask for people in the room who might go to the happy hour, the optional happy hour at the end of the day. Oftentimes people go to Southern Sun. There's also Illegal Pete's, and my children, because I told them we'd have dinner wherever we went, they're voting for Sweet Cow ice cream. So we can have a happy hour at any of those places. We can discuss it after lunch, but I just wanted to put in people's minds who are local, if you want to come to that, to figure out where we're going to go at 4, if you're interested. So without further ado, Dave Bailey, the Polar Climate Working Group Liaison, is going to present on this, and I'm going to take notes during the discussion here. I think we have the room mics on, so people in the room should be able to just speak.
Okay, thanks, Alice. So I'm going to give you an update of where we're at in the CSM3 development process. As some of you know, we go through this every 5 to 7 years or something like that, where we propose a number of new physics options for the next version of the CESM. And some go well, some not so well, and then there's a combination of all the components throwing all this together. So it's a process. So I showed this last year at the working group meeting. So you can see the timeline here, winter 2024, summer 2024. And these were sort of all the physics options that we were considering at the time and everything, the different levels of priority and sort of an approximate timeline. So I have an updated version of this figure. So I've now put this all onto 2025. See, that's why when we give timelines, we generally don't put a year on here. We just, it's winter, summer, fall, some year. Anyway, but what's sort of happened is that most of the lower priority things are really just going to get pushed beyond CSM3. We simply did not have enough time to evaluate a lot of these things. And it's unfortunate, you know, because in particular, the sea ice biogeochemistry thing, I mean, how many times have we pushed that forward? I mean, we keep pushing it forward. So, but we're going to get there. We promise sometime. But the main thing is that we do have at least 4 major physics improvements that we are going to be including in this version of the model. So the advanced snow physics, which you've heard talked about already, Elizabeth was talking about this, with, I say sort of, because with the caveat that, as Elizabeth highlighted, the grain size in the snow melt really causes the ice to become thicker. And so we weren't very happy with this. And especially as I was asking Melinda about with these summertime snow events, it would bump the grain size, you know, and we'd get higher albedo and we'd get really thick ice. So what we've done is we backed off to only the redistribution part. So there's wind redistribution. The pond improvements, you've heard David talk about. This is pretty much ready to go. We're going to start turning it on in our new runs very, very soon. And then the other thing that's basically complete is that Mathieu Plante had done some investigation of kind of congelation growth physics and was finding that we were sort of getting more frazzle than we should be, especially in thick ice areas. And so he has sort of readjusted the congelation growth process. And so that is also in there. Now, the one arrow that continues on a little bit further is the flow size distribution wave interactions, which you've heard Letty talk about. And we're close. I think we've got some promise there, but I think it's going to be, it will probably be, well, it's definitely going to be in there. It may just not be as tuned and as nice as we would maybe like the simulations, but we will have some form of flow size distribution wave interactions in the model. So the other thing I was going to talk about a little bit is this new post-processing package that we have available. It's labeled the CSM Unified Post-Processing and Diagnostics Package, or CUPID. And Mike Levy and Tegan King are really the driving force behind this overall project. Mike took this CSM Unified Post-Processing and Diagnostics, typed it into ChatGPT, and it came up with this cute little logo. So, but anyway, the idea is that, you know, we go through this CMIP process every 5 to 7 years or so, and we're always struggling to handle the large volumes of data that we have coming out of the model. We want to be able to put it into a standard format that we can share across all the archives and things like that. And so this is the newest tool that we have available to do this. And so it will do the time series, single variable time series file generation for all the components. And it will also produce diagnostic plots, which a lot of you have already seen before, but these are slightly different. And I probably don't have time, but I can talk to other people, give you a show and tell of this later. But here's kind of a sample of what we have coming out now. On the left here, this is sort of the traditional sort of plot that we always used to have, where you had ice volume, snow volume, and then ice area. And this is Northern Hemisphere for a couple of our long runs that we have. The thing that we've added, thanks a lot to Alice's input, is we've added the CSM1 large ensemble in the gray shading. All of those lines are the CSM1 large ensemble. And then the blue light lines are the CSM2 large ensemble. So now we can actually compare our CSM3 development runs to the previous large ensemble runs, get an idea of how we're doing. Not sure if anybody noticed this in the past, but look at this snow volume in the CSM1 large ensemble. I mean, it was really big. But anyway, we're kind of on par with CSM2 in terms of most metrics. But here's the thing that I'm going to talk a little bit more about in later slides, is the seasonal cycle of sea ice as compared to the National Snow and Ice Data Center extent. And that's in the upper right panel here. The black curve is the NSIDC. And now keep in mind, no, these are actually historical runs. So what you're seeing here is in the Southern Hemisphere, we're significantly overestimating the Antarctic ice extent in these runs. And you can just see, like in the summer, we're maybe a little low, but in the winter, we're way too high. And then we have spatial plots where we're also putting on the observed ice extent line, so the 15% contour on these lines. And I don't know if this is better. Anyway, but basically what you're seeing is the key region, I think here, where we're seeing the bias, so that winter extent bias is happening over here in East Antarctica, where it's really going way outside the observed boundary. And so we're actually going to be, starting up a sort of a task team to look into the processes behind this and develop a hypothesis for maybe why this might be happening. You're welcome to copy this link. It'll be in the presentation, and you can take a look and browse through all the new plots that we have in this Cupid package. And then what we've been doing to keep track of all of our runs is we have this new GitHub issues page where we're keeping track of all the new coupled runs. And so it's open to everyone. You can follow this here under the CSM Dev issues GitHub. And it just lists all the runs in terms of who did them, where the data are stored, and how long are the runs, where are the diagnostics for these runs, and that sort of thing. The latest run that we have both pre-industrial control and a historical run is this 121 in the series. And yes, we've done 121 development runs so far. CSM2, I think we got over 200. So there's still more to come. But anyway, this is the latest with a pre-industrial control and a historical run. So then again, looking at a little more detail in that first plot that I was talking to you about, this is comparing the 121 historical run with one of the earlier historical runs, 104. You can see here, in general, we're kind of close to the CSM2 large ensemble in the Northern Hemisphere, at least maybe a little closer to the CSM2. We're definitely well below the CSM1 large ensemble in terms of our snow extent and so forth. So overall, I think the story in the Northern Hemisphere is that we're doing pretty well in most of our runs so far. And again, I think just looking at the spatial plot and the seasonal cycle, yes, we're probably a little low in summer, maybe just a touch too high in winter, but overall, it looks pretty darn good in the Arctic in terms of the seasonal cycle. And David alluded to this, but we've also been looking at these with the ponds turned on as well. We have another historical run that's only up to about 1947 or so. And then similarly, sea ice thickness, you know, I mean, we can compare to some products like biomass and things like that, but basically here we're just comparing the annual cycle of thickness to the annual cycles from the CSM1 and CSM2 large ensemble. And again, we're sort of closer to the CSM2 large ensemble, which is kind of good, but also, you know, CSM2 was a little thin in the Arctic, so maybe not so great. And keep in mind, again, you know, these are still development runs and they're varying lengths and things like that. And so it can definitely be a little bit of internal variability in terms of what we're seeing here. So the other nice thing that Alice has added to this too is some box plots to give us some more quantitative metrics of these things. So on the left, what we have are plots of sea ice area, again, compared to NSIDC and the large ensembles. And then on the right are just the box plots, which give you an idea of where the median is, you know, where the two standard deviations are in terms of the simulations and the variability. And then that can give you a much more quantitative answer to say, okay, well, we're much lower than in, for example, the sea ice volume in the Northern Hemisphere, we're well below the CSM1 large ensemble. You can see that as in this sort of a metric. And then similarly with the snow on the sea ice, we're kind of closer to CSM2, which I think is a good thing. I think from Melinda's paper, we were actually doing pretty well in terms of snow on sea ice in the Arctic. But I'll have to touch base with you on that one as well. Southern Hemisphere is a little bit more of a convoluted story. I probably need to speed up here, so I'll just kind of skip over this detail to get to this. But basically, yeah, as I said, most of our bias is happening here in the East Antarctica, where we're way outside of the sort of observed boundary. And that's the winter maximum problem that you're seeing here in the seasonal cycle. Summer, maybe we're melting back a little bit too much, but it's still, in general, the summer's probably much better. And I think I see a whole bunch more slides here. But I think, again, the whole point is these diagnostics give you a lot of more quantitative metrics that we can use here. Okay. So we have time?
Yeah.
Okay. Okay.
I guess I'll take over here. So the
Yeah.
CSM Antarctic sea ice is a showstopper, we think, for us. I'm going to go back here, which is looking at these box plots. So you don't really have to worry about the 104, the blue plot, but the 121 is red. And that we're trying to just see, like, how wildly large this is during the September sea ice mean. And so it's just way outside the bounds of not only observations, but either of the other large ensembles we did. And so we've talked about this ourselves. We want to bring this to the attention of the whole community because, for us, this feels like a showstopper. The CSM2 Antarctic sea ice was pretty good, but this is really not physically realistic. It should affect the whole global climate in terms of like the ocean, the atmosphere circulation. And so one of the things we want from you guys is feedback about how this bias would impact your ability to do science, because we've tested a lot with sea ice albedo tuning and some cloud mod testing, some ocean mod testing. We haven't been able to fix it really at all. And so that's why we want feedback both from the outside community and then some of the people from CGD are here also, because I think we need help from other working groups. So we kind of have sorry, I feel like I got real loud all of a sudden. We kind of have 4 hypotheses about maybe what's going on. This is really a winter problem. So it's like June to October when the ice gets really extensive. So the first hypothesis is maybe there's cold ocean temperatures, and this could lead to excess sea ice growth, either farther away from the coast than we expect, or maybe it's not melting the water or melting the ice as it gets advected northward. The second hypothesis is maybe a little more atmospheric. If there's zonal winds that are too strong or a shift in the jet potentially,
then maybe this is leading to excessive northward Ekman sea ice transport. Hypothesis 3, we've tried to test this, but could cloud cover biases that impact radiation lead to a cold surface bias and therefore ice growth or lack of ice melt? And then the 4th is maybe there's too much precipitation and that could be leading to excess sea ice growth from either snow ice formation, freshening the ocean, potentially cooling the ocean, something like that. So we've started to look into these to try to understand, and this is just a preliminary, I've looked at all the Cupid diagnostics for other components for 121, but I'm not trying to point the finger at any other component, and I suspect this is actually more of like a coupled bias, like something kind of gets a little out of whack and then it gets reinforced. But here's what we've started to look at originally. So this is looking at temperature biases in the ocean. This is surface temperature, and it's just the Southern Ocean. So you can see the spatial plot up above, and anywhere there's blue, there's a cold bias in the ocean, and this is compared to observations, I believe. And then this is looking down, it's averaged over the whole Southern Ocean. But you can see that there's these these cold biases here, like in the East Antarctic, where we get that really extensive growth. And then there's what we're kind of calling this curtain that's blue in the Ross Sea, which is not an area that we have such terrible extensive biases, but maybe is connected somehow. So trying to understand what's happening in the ocean here. And now this is looking at depth on the y-axis and going north from the continent. And you can see that this cold surface bias extends pretty far forward, but it's not just at the surface. It goes down, to at least 1,000 or 2,000 meters in many places. This is the corresponding salinity biases. So blue here means that there's a fresh bias. You can see that it's fresh like everywhere. And it's very much in the upper 1,000 meters. This is the same sort of zonal plot where you're going north along from the continent, and you can see that it's very fresh in the whole Southern Ocean. So this is kind of the first step, looking at the ocean biases to see if that could be contributing to what's happening in the ice, and the ice might be reinforcing these as well. Like I said, it's a coupled problem, probably. We also tried to look at some of the atmospheric fields. So here, what I'm showing here is the total cloud fraction, and we're comparing it to ERA interim. I'm not sure if that's really a good truth, but anyway, green here indicates higher cloud coverage in CESM3 than ERA interim, and you can see around much of the continent, it's green, so there's a lot of cloud cover, and you can see that here too when we look at this zonal plot where CESM3 is, this test run is blue, and you can see there's higher cloud cover than in ERA. So maybe the clouds are part of this. We looked at the precipitation. Here, red, again, this is the CESM3 minus ERA. Anywhere it's red, there's more precipitation. And you can see that too in the zonal plot. So maybe precipitation is contributing to this as well, though at the extent, I'm not sure. And then we started to look at the winds as well. And what we're seeing here, again, this is just at the 850 hectopascal level. I did look at the surface winds, and those were, you couldn't really see a signal. And I think if we look a little bit higher, it's a better indication of what's going on with the jet anyway, than just the 10-meter winds. But what you see here with CESM3 minus ERA 5, anywhere it's brown, is slower winds. And so you can see close to the continent, it actually looks like the winds are slower. But when you look at this plot, as you go forward, as you go along the x-axis, again, we're looking northward or equatorward with latitude. Maybe there's some sort of shift in the jet compared to ERA interim. So maybe it has to do with the jet shifting, and this is just an indication of that jet moving northward. And then we've looked at the CVDP package as well. And I'll just point out that, I'm sorry, this is actually really hard to see, but the first 3 in the top row are ERA interim SAM patterns, and then CESM3 is this top right one, and then I think these ones as well. And then CESM2 is the rest of these. And the main thing that I'm pointing out is just, it looks like there's a shift, at least from CESM2 in what's going on. So maybe the SAM is impacting it. That was kind of where we got to just with the ice side of things. And so I guess what we're really looking for is if anyone else has ideas about how to handle this, we'd really appreciate, working on a task force or feedback from the community or feedback from other working groups, because we don't think we can just fix it on the ice side, but we think that it's it's really not ideal for releasing the model this way. So I think that's the end of the slides. And I wanted to open up discussion. And I think we're going to put all the virtual people, your faces will be tiled here if you want to turn on your cameras. But I think the discussion, if people have ideas about these biases, that was one thing we wanted to discuss. And then the other thing was when we do release CESM3, coordinating on different types of manuscripts. So I wanted to be able to talk about that. You know, do we want, I think some of the new physics that are going in, there will be some manuscripts on that, but if we want an overview paper, or if anyone else is planning things, just to try to understand what people are interested in, what their plans are, so that we can talk about it. So I think we're done with the presenting. I'm going to turn this off and we'll just use the roof mics, and maybe Dave can you moderate and I'll take notes as people talk. Okay.
Yeah.
And people online, you are on the screen now.
500 and even 300 millibars, just in terms of your basic jet. But I think, you know, the fact that SAM has sort of shifted, which I think is sort of hard to do in the model, to see is because it's been pretty consistent, tells me something that might be something dramatic going on with the variability. And so you might want to look at not only decadal, but also interannual modes of variability, such as, you know, PSA 1 and 2 versus SAM. And you also may want to look at, I mean, there's a lot of different teleconnections you could look at to try to hone in where you're getting the biggest differences in your variability, for example. And I think that could be a clue if it's an atmospheric problem.
It sounds like you're volunteering.
I'd be happy to help.
That'd be wonderful. So, Isla.
Yeah, I just want to corroborate what you're saying about the jet. I think it's gone from being too strong kind of in the Drake Passage region before to now being shifted equatorward, so that it's actually a bit too weak at the ice edge. So it sounds like that's not in the sense of, I guess I don't know, would an equatorward shift not be in the sense of?
I think if it's less at the ice edge, then you wouldn't get as much northward Ekman transfer. But the hypotheses were just like, okay, what could be causing
Yes.
this?
Yeah. I think it's kind of gone from being more biased to being less biased. Oh, it's still biased, but in a different way. So
Right.
I was wondering if do forest ocean sea ice simulations help at all, or is it just too constrained by the temperature forcing that you give it? Would that help to isolate if you have atmospheric forcings correct?
I think we've looked at those. I mean, Gustavo's got a number of the forced simulations, and I don't believe they have the same Antarctic bias, but yeah, Marika.
Well, but when you prescribe air temperature, you constrain it so heavily that, you know,
Exactly.
even if your
Yeah.
ocean is biased, you can
Right.
kind of counteract that because you just have this infinite capacity
Right.
atmosphere.
I was
So
thinking,
it's hard to use those to.
yeah, I was thinking to add on to what Alice said. I was thinking the opposite may be true too, where if we're not transporting enough ice northward, where, you know, it's sort of sitting there in the colder waters instead of being ejected northward into the warmer waters, then that could also be a problem. So, yeah, still things to be looking at. So, other thoughts online?
Another question.
Sure.
How long are these simulations?
Alice showed the historical run, so they're 150 years basically. So
And there isn't like because I think it was CSM1, right? Where we shifted from I think it was more northern hemisphere, but from a high ice state to a low ice state. You know, there was like, you know, periods of 50 years where, you know, the ice was like reasonable and then it was unreasonable. This was like, I think, in the 2-degree model, but I was just curious if you see anything like that as consistently high. You know, like is it because we haven't run it long enough?
oh, I see what you're saying. I mean, CSM1 was biased in both hemispheres, actually.
Okay.
Yeah, it had pretty large extent in both hemispheres. CSM2 had a great Antarctic ice extent, but the Arctic was too thin. and not extensive enough. So, you know, so it's this interplay between the hemispheres that could be really challenging. So Marika, you have more of that.
Yeah, well, I was just gonna say, this has been a very consistent bias among all the, you know, the recent runs. So I don't think it's just this 121 run not
Exactly,
going long enough.
exactly, yeah.
It's been in kind of, I don't know, maybe the last 20 runs or something. It may have been there much longer,
Right.
but we've been focusing on
Yeah.
it more recently. So it's not, I mean, it could be related to the length of the run and spin up and things like that. We do see really long time scales in the Antarctic in terms of spin up,
Right.
but I think it's a real bias. I don't think we're gonna get away from it just by running longer.
Yeah, and I think I said it earlier, but the 121 it's the longest run we have. It's 200 years. It's not necessarily the control we want to go with, but yeah, so at least that's where we focus our efforts for analysis. Bill, you have a thought?
Do other Mom 6 users like GFDL see anything that looks like this?
That's a great question. I really don't know.
I think in the GFDL spear model, we definitely see like the same seasonal bias pattern in the Southern Ocean, like too low sea ice in the summer and far too much sea ice in winter. I think it's more of a, I think it's more of like a hemisphere-wide bias in the ice edge rather than that kind of like East Antarctic region. In the winter.
Yeah.
I need to double check.
Yeah.
I do think what we're seeing, it seems like it's most noticeable in East Antarctica, but you can see it's more extensive in
Right. Yeah.
all
Right.
around too. So,
Right.
yeah.
Yeah. Well, that's always the problem with Southern Hemisphere is that it could be biased northward by a little bit, but if it's stretched around a big area, that integrates into a large amount. So, yeah, Isla, you have some thoughts?
Yeah, I was just wondering if a nudged atmospheric run would be helpful and could at least
Yes.
point towards.
Yes. Yeah.
If, I guess if the bias is still there, in that case, it tells you something that could be fixed in the ocean.
Yeah.
Sea ice side.
Yeah. Very good.
I feel like that would be useful for many things. So maybe
Yeah.
try and do that.
Yeah.
Julie.
I've noticed the SAM variability is much larger in CSM2. I don't know how that might get more positive, extreme positive SAM, maybe that would push the ice edge further. But I don't know what would cause that. And then the connection to the tropics seemed weaker as well. So I don't know if maybe the ENSO bias is.
Really, was that in CESM2?
CSM2, the SAM variance was much larger.
Right.
Than CSM1.
Right. Yeah. And I can't really speak to ENSO and the CSM3 runs. We've been finding a lot of differences in each of the runs. We change a few things and then it changes ENSO. And so I'm not even sure where we are at this point. I don't know. Isla, Adam, you have any?
But I think that's a good point that it could be some sort of teleconnection.
Yeah.
as well,
Yeah.
Impact.
Although the cloud cover seems critical. I would have thought.
Yeah, what's interesting too is one of the runs Adam did was he changed the ice cloud radiative properties, and it had a bit of an impact on the Arctic, but it didn't change the Southern Hemisphere at all. So
Super cool with liquid cloud, right? In the summer.
I guess there's just more liquid cloud in the Southern Hemisphere is I guess the problem. Yeah. So yeah,
I guess one thing that's been pretty clear in the CVDP is just way more variance in the Southern Ocean SSTs. And I don't know if that's just because it's a thinner layer or if there's something that would really be impacting on the sea ice related to that. But that's right, Adam, that's been pretty clear.
Yeah, that's been pretty consistent.
yeah, that's interesting. Yeah. I mean, that is something to highlight about MOM. For those of you who aren't aware, it's a level model. And so we're not fixing it to these Z levels that we had in the previous versions with POP. And so, and because of that, we've allowed the upper layers to be 2.5 meters thick instead of 10 meters thick. So that's been a big change with this version of the model.
All right, well, I know we are unlikely to solve it here, and I had talked to the Ocean Model Working Group folks, and they're both out this week. So we'll bring this up if anyone else in the community outside of NCAR, within NCAR, wants to talk about it more. We'd love to talk about it because we're trying to sort this out, because I think we want to, there's pressure to start CESM 3 runs and kind of finalize the model soon, and this is something that we haven't been able to improve despite some attempts to do so. Yep.
I'll just say, I really like the idea of a nudged wind
Yeah.
run. And
Yeah.
I think if multiple working groups advocate for this, that could be helpful at maybe actually getting it done, because I think that would be really helpful for us in terms of figuring this out, but it might be very useful for other aspects of, biases in the coupled system. And so.
And if only we had that expertise in the room.
Yeah, I mean, I think it's just a case of interpolating all the Euro 5 to the SE grid and running one.
Yeah.
Just.
All right, we'll bring it up at a project meeting as something that came up as a possibility. All right, any other thoughts about the CESM 3 development biases? Tomorrow, or not tomorrow, this afternoon, we're going to talk a little bit about post CESM 3, so what we're planning for future stuff. So we haven't forgotten about it, but that's kind of the afternoon discussion, one of the focuses. All right, so yeah.
One quick, I think we will need to tune for the Arctic as well. I mean, the Arctic ice is a bit too thin and stuff like that. I think albedo tuning works pretty well in the Arctic, and so we probably can do that. But we shouldn't forget that the biases in the Southern Hemisphere are so big that they're occupying our attention, but we also need to, there are improvements we should make in the Arctic simulation too.
Yeah.
So just want to make sure that gets
It
noted.
feels like that's something we can actually.
We might be able to
change,
do,
whereas
yeah.
Yep. Okay. I think the next topic was thinking about manuscripts, just to kind of start it off. I was going to say, oftentimes when we have a model release, there are kind of overview of manuscripts. So we were thinking about having at least one like polar climate overview manuscript talking about, what the polar climate looks like in CESM 3, how that compares to CESM 2 or 1, and observations were relevant. So there's kind of that manuscript, and if you're interested in contributing to that, it might not be focused on, say, snow, but there would be like a small section about snow. But there's often also, when there's been a release, a number of like specific, more focused manuscripts about, what does the snow on sea ice look like? Or I don't know if David is still in the room. I actually don't see him, but
Yeah.
David, is, I would assume, going to lead a paper about the sea level ponds, and Letty and Cecilia might lead a paper about the flow size distribution and stuff like that. So we wanted to just talk among a whole working group about who's interested in either contributing to a manuscript or leading a manuscript. I don't have any information yet about where special issue might be located. I haven't heard anything from David Lawrence, the chief scientist, yet. But if you have any plans that you're interested in sharing, that way we can just, we can have a smaller mailing list about who's working on manuscripts and be able to email you more directly. So, and we also talked about the possibility, like, even within NCAR, there hasn't been a lot of coordination sometimes with the Polar Climate Working Group and like the ocean section to look at the Arctic ocean behavior, for example. And so we're interested in, like, maybe that's something that we need to bring in more, especially with MOM 6. I think that might impact our simulations a lot. So yeah, open mic here. Maria.
So I like the idea for this, and I'm not volunteering for it. But I think, ENSO's been brought up, the SAM's been brought up. It would be interesting to have a paper on modes of variability and their impacts on Southern Hemisphere sea ice cover. And so, I don't know, looking around the room, it may be some people that might want to lead something like that. I think it would be No one else
pointing
is
at people
volunteering
too.
either, so.
I think she's pointing back at you.
There's a nice group here that could write that paper really well. I'll just mention David Clemens Sewell does want to write a sea level ponds paper, so even though he's not in the room, we can put him down for that.
Yeah.
I think both CC and Letty, yeah, they both had.
Yeah, they both had.
But I believe they are also planning to have some sort of paper. As Dave alluded to, we're not sure which wave fracture scheme is going to be in CESM 3. I know Letty presented on 2, and it might be the not as good one just because we're more familiar with it. So there might be a paper that compares those other wave fracture methods or something. So that could be a future wave method. We're not 100% sure yet.
Yeah, this is Alex. So just to add, following on from our presentation here, we're more than happy to kind of extend some of the comparisons that we've done to support any of this where needed to. And yeah, we've just been talking offline about trying to set up scripts to be able to bring in different CSM outputs to kind of produce similar plots to ones that we already have. So yeah, let us know.
Are you gonna idle it down the rabbit hole?
Oh, we're going to go deep down the rabbit hole. Yeah. And then, yeah, I had a question. So you kind of have mentioned things like the kind of doing some retuned runs. Is the idea that you might do something like the CSM less melt kind of study, but kind of more quickly this time? You know, it might be a more quick follow up to kind of retune sea ice.
Maybe. I mean, I had, again, this afternoon, I was going to talk about what sort of community experiments we want to do, but we could start that conversation now too. So I don't have all the numbers on this slide right here, but at least right now, I believe we've been told by David Lawrence that there's not currently plans for CESM for like NCAR resources to be used for a CESM 3 large ensemble. And so there's at least been some discussion among working groups to try to pool resources to have some sort of CESM 3 medium ensemble. I don't know the 100 runs because CESM 3 is pretty expensive to run. There's also, you know, we were talking about nudged runs. Is there interest in having some sort of nudge, like coordinated polar climate working group nudged runs? I feel like our working group has especially used that tool to understand physical processes and model and stuff. So that's an idea that I had. During the last allocation, Polar Climate Working Group led the CESM2 CMIP5 community experiments. So those were CESM2 experiments, but they used CMIP5 forcing so that you could kind of, by comparing the CESM1 large ensemble, the CESM2 large ensemble, and then the CESM2 CMIP5 ensembles, you could see what the impact of model versus forcing differences were on the results you were getting. And I don't believe there's any plan to run something like that with CESM3 yet, where CESM3 with CMIP6 forcing. Let's see if I can get my numbers right here. So things like that could be an option. Yeah, Isla?
Yeah, I just said that experiment is being proposed in DAMIP as an actual CMIP.
Okay.
Okay. Okay.
So it would be great.
But do you know too, I mean, we're probably not going to have all the CMIP7 forcing in time for fast track and maybe even some of the deck experiments. So are you still going to be running the CMIP6 forcing there?
No, they'll be run with CMIP7 for.
Oh, okay. Okay.
Yeah.
The forcing is frozen as of last week, except for the ozone and nitrogen, which is ready by May.
Okay. Perfect. Perfect. So, and Alec, just as an add-on to what Alice said, I mean, I think the motivation for the less melt experiments was because the Arctic ice was so bad in CSM2 that we had to say, look, you know, if we had had chance to retune the ice, we could have had much better experiments, you know, and so hope is that we won't have to do that with CSM 3.
Yeah, and I was wondering if you guys had, kind of a threshold for that in your heads a little bit. But yeah, I guess these things are always a bit up for debate.
I mean, we're always under this constraint of the whole project in terms of when a model has to be frozen or when decisions are made. So
yeah,
I think if we are planning in advance, that's something we need to do. I mean, the thing is, the atmosphere is still changing, the ocean is still changing, so we're not at all in a situation where we have sort of a final version of other components that we can tune underneath. But I think we have some experience with how to tune the Arctic sea ice cover. Those last melt runs being some of that experience. And so I think the hope is that we can use that experience to tune the Arctic sea ice fairly easily.
Yeah.
But we'll see. There's big differences in like the snow on sea ice and stuff like that.
Yeah. Well, I think that was sorry, go ahead, Alec.
I was gonna say, yeah, so if you did like a nudged run and then people evaluated that and were like, well, actually the nudged run is really good. How does that then inform what you might do in terms of like a model retuning? Because then it gets a bit more hard to motivate that, right? If it's
Well, I mean, I think then we have to ask the atmospheric model working group to help us improve the winds, which I guess is, I'm looking at Isla, that's not a very easy thing to do necessarily.
Right.
But it at least points out that, I mean, I think it's easy if there's a bias in the sea ice model, in the sea ice simulation, to assume it's a bias in the sea ice model. That very often is not the case, right?
Yeah.
And so we can,
Yeah.
so at least it gives us some insight onto what biases are impacting the sea ice and where we might have room for improvement. That very likely won't be the sea ice model.
Mhm, right.
So, but I know it's not easy to just tune the model to change the location of the jet, right? Otherwise, we'd have a perfect jet, right? So, but
I was going to highlight that we have these weekly sort of ish project meetings, and absolutely everyone is welcome to join. So if you're ever interested in tuning in to sort of see where we're at with that process, please, just contact one of us and we can give you the link for that. But I was going to add on to that I think Dave Lawrence said that, he's mostly concerned about the quality of the model simulations and does not want to do CMEP simulations with a bad model. So I think as long as we keep harping on this Southern Ocean issue, that this is a showstopper, then hopefully, this is something we can definitely improve before those CMEP simulations proceed.
I guess I also want to say especially for the atmosphere diagnostics or CBDP, if there's a coupled impact, we know that the sea ice impacts like zonal wave pattern 3 and stuff like that. So the sea ice is likely degrading some of the other aspects of the model. Like maybe the sea ice is part of why the SAM looks so weird. It might not be the SAM forcing the sea ice, but something like that. And so being able to understand how, to us, what looks like a showstopper problem might be impacting other parts of the climate would be really helpful, I think, as well. And especially in these project meetings, for bringing it forward as like we really need to figure out what's going on here as much as possible type thing. So that was why I had the will this impact your ability to do science with this model? I think, as Alec presented earlier today, when they're doing their comparisons, sometimes they just throw out the bad models, and we really prefer CSM3 not just be like, well, that's a bad model, throw it out.
Ready to throw it out. I'm ready. Yeah, exclusion is a harsh word, I guess. We need a softer word. Gently put to one side.
Any other thoughts?
Qinghua, I saw your cameras on. If you have anything you want to say, we want to make sure that you can speak up too.
Yeah, thank you. Very nice organization of the talk. I heard the first one yesterday. So I was also learn a lot, just like the CSM, because I did a nudging run. I focused on the Arctic sea ice, and I did a nudging run, and for the CSM1, I observed a pretty good sea ice simulation, but by using the same setting in the CSM2, it seems like the trend is gone, right? And I somehow realized the same problem, just like I saw that the CSM2 is too sensitive to the heat transport, like a polar forward heat transport somehow. I don't know how to test that, but now I have some thought to do this, to do some testing, but maybe I will do this for the CSM3, just like when we do the nudging, we can not only nudge the Arctic, but we can do this in the CSM1. I don't know why. Just if I do the nudging for the CSM1, I only need to nudge in the polar region, just like Arctic, like everything beyond the 60 degree north, if I focus on the Arctic sea ice. But for the CSM2, if I nudge in the same domain, it seems like that there's a leakage of the wind to the to the lower latitude, and that drive something and make something very different. I don't know. So now I think that even with future with nudging the CSM2 or CSM3, we should be really careful for this nudging, how we set the nudging wind, because even we just put like a CZ ERA5 wind in the polar area, but dynamically there's maybe continuity conservation everywhere. We'll feel the wind in the polar, then because it's observed wind, right? And over the past 40 years, we observe the tropical cooling, slight tropical cooling, right? So this information in the polar will just there's a leakage there. So the wind will influence the North Pacific, and North Pacific will drive this big gyre, and the big gyre maybe will generate some cooling there, and this cooling will quickly spread out everywhere and get something. So probably in the next step, I'm interested to do something just like when we do nudging, we can test a different nudging scheme, just like one thing is just like the nudging the Arctic only, and like the other place is freely integrated. Another one is we nudge in the Arctic only, but out of the box, out of the Arctic region, we can fix the wind, just like put like a 1979 or 1979 for 40 years, or we change it to like a 2010, 2001, or something like this. That's like a mixed wind pattern. There is we also when you set some like a transition zone between this different year wind, we just mix the different year wind together, something like this. So this is something I learned from my nudging experiment for CSM2. I saw the same result as I don't remember the speaker, but she gave a really good talk. The first one yesterday. So I really saw. Yeah, I saw the same result as her. As her stuff, just like if I give the same ERA5 wind, no trend, just like it's a flat. But we test a different setting, just like we give a ERA5 wind, but make the outside of the Arctic region, the global domain with the other wind. Just we don't like a wind to reintegrate it, just like we give like a 1979 wind 40 years. We see the very similar result as a CSM1. So it seems like there's a very different sensitivity to the forward transport of the either heat or like the momentum or like a moisture, something very different from CSM1, CSM2. So I thought CSM3 maybe have the same issue. So I'm just really interested to see how the CSM3 looks like in terms of transport of this stuff. Yeah, thank you.
Additional thoughts on that, Esther? Yeah, I didn't mean to put you on the spot, but I just did. So.
Not at the moment. I did know that like when we compared winds outside of the nudging bounds in CSM2, they were definitely differences. So I can maybe agree with the, linking of winds to lower latitudes. At least for the Meridiana wind, that was where we saw the biggest differences. Didn't see that really for the zonal.
Cool.
seems to support having some CESM3
Yeah,
experience with
absolutely.
different nudge wind.
Do we think the infrastructure is basically the same for nudging and CSM3? Has much change there?
I think it's the same. We just need to, I mean, Julio and I have been working on this scripts to get it Euro 5 on the SC grid.
Got it.
But yeah, Patrick's nudging code works. It's
Perfect. Great. Any other thoughts online?
Different topic, just a brief advertisement and reminder that CSM does have data assimilation capabilities for sea ice and land and atmosphere and ocean. You can run the model coupled and assimilate into one or more of the components. So if you have short-term kinds of phenomena that you want to investigate, that's available and we're happy to talk to you. There's also a 10-year ensemble reanalysis of atmospheric forcing for the surface components. So that can be useful too. And that's it.
Have you run DART with CSM3 yet?
No, I'm working on getting it set.
Courtney, do you want to look at biogeochemistry and CESM3? See if the
Of
coders are
course.
alive.
Yeah, definitely. I think one interesting thing that I'd be super curious to look into is we have observations of big under ice phytoplankton blooms, which the former melt pond scheme may not have allowed sufficient light to allow those to form. So I'm really curious to potentially use this revised melt pond scheme and see if it allows for more phytoplankton blooms under sea ice.
I wonder too if the float sizes would, like if there's any impact with that too. I don't
Yeah,
know.
there's certainly ideas that leads allow might like allow for the generation of these under ice phytoplankton blooms. So that would definitely be interesting.
Sorry to put you on.
No,
Yeah.
I'm very curious.
Have you had a chance to look at this, the newer Marble model yet? And so you have a sense of what things are available. I mean, we don't have the coupling between the sea ice and the ocean yet, but at least we could start up simulations with Marble turned on.
Yeah, so I've been looking at a lot of runs with CSM2 and at the most recently at some of the 4P2Z Marble runs. The big challenge is to get an estimate of productivity under sea ice. You need like a lot more daily output than is
Yeah.
maybe typical.
Yeah.
But luckily Alice did a run for me that has the daily output needed to look at under ice productivity. So very cool.
I mean, I think this just means we should, whatever runs David wants to document the sea level ponds,
Yeah.
we should make sure that the right BGC fields are safe so that you can,
Absolutely.
Right,
use those to look at the BGC impacts. And
right.
so we
At
just
this
need to make
point-
sure we're coordinating appropriately.
At this point, my understanding is we have not turned on Marble yet in our standard runs. So that would also have to be added.
Minor details.
Just a small detail, yeah. Yeah, microscopic. Ooh,
Going back to the Southern Ocean sea ice bias. So, yeah, America is true. The ocean sea ice configuration of the simulation is really constrained by air temperature. But that region is kind of where the eddy heat transfer is kicking in, I think. And, the mixing scheme is quite different in MOM 6 compared to POM.
yes.
And air temperatures, I think, I don't know exactly, but around freezing point or so. So little change in the ocean temperature can make some difference along the ice edge. So it's still worth checking sea ice ocean simulation.
Thank you.
So actually, I had a question, because you gave a really nice talk at the Ocean Model Working Group meeting on the Atlantic layer and what could be controlling biases in the Atlantic layer within the Arctic. So are you planning to look at that in CESM3 at the simulation of the Atlantic layer, or is your work on that topic coming to an end, or, yeah? Because that would be of relevant, I mean, I think there would be interest here in seeing how those biases in Atlantic layer affect sea ice, as well, so.
Right, so at the end of my talk, I show just one slide from CSM3, so the Atlantic layer bias is still there in CSM3. I don't have specific plan to look at it, but I can further look at if necessary and times alone.
Yeah. I mean, if there's if there's an Arctic paper, if you even just contributed a little bit on the Atlantic layer simulation, that might be really nice, so.
Yeah,
Okay.
I think I can do that, yeah.
Okay.
Thank you.
Sorry, I volunteered you. You can later tell us no, I can't. I don't know.
Well, yeah, I was kind of thinking when you discuss about this joint paper, of course, I think Gustavo will write ocean description paper, but if we find something interesting in high latitude, for example, if the sea ice change is more related to ocean model change, then we can probably write a separate paper. But I'm just, yeah. Yeah.
But you would be willing to maybe if you're not leading, you'd be willing to contribute. And maybe you would lead, depending on what the situation is.
Or maybe if there's an ocean paper, we contribute to that. the ice
If
analysis
there's
or
just an
something.
Arctic section in there, yeah.
Whether it's
That's
led
a-
by
that's a
the
great-
ocean group or
Yeah.
led by polar. But yeah, be nice to work together on some of those things.
Yeah. Yes. Yeah.
All right, so I'm just, my clock says 11:33 now up there, it says 6:57, so I don't know what that's on. But, I guess if you don't mind, people who might be interested in contributing to a community paper, can I just get your name so that we could, contact you in the future? You don't have to make a commitment. Make a commitment today. 6 easy payments. No, I'm just kidding. You don't have to make the commitment today. And I know there's a lot of uncertainty about how, what will be funded to do in the next period of time. But if you might be interested in contributing, we would like to know just so we can kind of start coordinating and figuring this out. So you can even raise your hand like just a little bit. And I already saw you, Alec, you already said you would, so I'm adding your name.
Linda had a hand. Julie's little hand. Christine, little
It's a
hand.
motor variability paper.
Okay, sounds good.
Yeah, I'm happy to contribute.
Yeah, awesome.
Well, there was just about modes of variability in CS.
Excellent.
I know where to find you.
I send you.
All right. Well, we ended the last session early, late, but now we're like 15 minutes ahead of time. So I think if there's nothing else people want to bring up, we keep you here longer, have a slightly longer lunch. That sounds
Sorry,
okay.
I do have something I want to bring up.
Okay, bring it up, Constance.
Okay, I'll bring it up. So in terms of some of these questions about what is going on with some of the nudging rods, I think it could be really useful to do some sort of analysis of like teleconnections, polar, extrapolar teleconnections in terms of, CSM1, CSM2, CSM3 observations, just to get a sense of how our different models are looking relative to, the limited observations in the real world. I think that can be like really instructive for some of these questions. Like, for example, in terms of some of these nudging experiments, like I'm really curious about, you know, like energy transports and, you know, how that is partitioned into the polar regions in these different models. So I think that could be worth doing. Another really weird thing that I was just thinking about is that usually we always have issues with Arctic sea ice if you look at it wrong and it's messed up, but this is like very strange that it's Antarctic. So I don't know. I'm kind of, I feel a little more concerned about this because the Arctic is usually the problem. So I don't know. And often, you know, that tends to be kind of like an AMOC thing, you know, sometimes, you know, cloud things, deep water formation. I mean, that always is an issue, but this is just strange. So I don't know. It's just like amusing. And then, yeah, which is weird. And then the other thing I was thinking too is like, you know, somebody else brought this up too, the long time scales of the Southern Ocean. I think we should really think about that in terms of looking at these different shorter runs, because it's possible we're in a cold state, y'all. So I just want to know that we're not before y'all put in a ton of work to fix this, you know, because the fix might not really be needed because we just, maybe it was a cold start. I don't know. I don't know. Y'all know this better than I do, but just thinking about those long time scales of variability that we know characterize the Southern Ocean. Like, is there any indication that that could be it?
I have a partial answer. We've done different experiments, 1850 PI, with different initial states in the ice and ocean. Most of our experiments we tend to do, we use an already sort of spun up coupled state there. But more recently, we've started using the initial state from an ice ocean forced run. And those ones actually have the colder pressure state. And in fact, we're seeing our great friend, the Labrador Sea freeze over happening again in those runs. So, you know, yeah, it's, there's definitely the interplay there of those things. But I think, and to highlight what I said earlier too, you know, we did a PI run and I think we only initialized from year 87 or something, but then we did a 150-year historical run. And I think that's going to sort of alleviate the initialization problem.
Yeah, I mean, the thing is, like with CSM2 large ensemble, right? Like the Northern Hemisphere was sort of prioritized in terms of getting, you know, an assortment of initial states rather than the Southern Hemisphere. And so I feel like often the Southern Hemisphere is a bit of an afterthought. And so.
Yeah, totally.
Yeah. Because, and so I'm just wondering, you know, it's like, okay, we started from different initial states, but were those initial states actually substantially different in the Southern Hemisphere versus the Northern Hemisphere? I don't know.
I think that's a good point. I mean, we have run many years of different PI states, and I think that's kind of why we added those box plots to the Cupid diagnostics that Dave showed earlier, is that like what we're seeing is totally outside the bounds or is never within the bounds of either of the previous large ensembles or, you know, or the observations, which I know are not pre-industrial, but still, like, we really think that there's something funky. And I think we have, you know, we've tried to see is there ocean drift. I mean, at least in previous versions of the model, it was like getting warmer, but that must have been at depth in the ocean. But I don't know if that's still going on, to be honest. They've been trying a lot of different things in the ocean, I think, to messing with the mixing a lot.
Yeah.
I'm guessing what Who said might be part of this. Like, it's hard because we're going to an entirely different ocean model, and a lot has changed, and figuring out like what if that is in fact driving this, like what is the primary impact, I think is proving to be challenging. But I think what Will said earlier, maybe we should double check with others at GFDL and see, is this something that happens more often in MOM6 in general? Hopefully we can figure out a fix.
Yeah, I mean, my understanding is MOM6 usually has the same Labrador Sea issues, but I don't know if anyone has, or I don't know who has looked in detail in the Southern Ocean in terms of MOM6.
Yeah.
but that would be useful, right? So that you're not kind of generating all of this information about biases from scratch. Yeah, because this model, I mean, it's relatively well known, I guess. So yeah, we should probably maybe talk to those folks.
Yep.
I think that is generally what, I mean, GFT are going through like a new development phase for the Ocean Sea Ice model. So 5 development, and I think the Southern Ocean and the sea ice there does feel a bit twitchy. It changes. I think like, you know, Mitch is putting in this like new ridging scheme into SIS2 there, and get some crazy sea ice thickness patterns coming out when you put that aside. So I don't know that it does seem very sensitive, at least in,
Yeah.
I don't know if that's coming from the ocean.
Yeah. Can we see the chat for a second? I think Elizabeth Faircloth had something she put.
There is a red notebook and 2 water bottles.
Oh, okay. That's, never mind.
So if you're missing things,
Yeah,
go to the
okay.
front desk and check. All right, well, we are kind of close to actually 11:45 now. So are there any final concluding thoughts? David, we volunteered you to do all of the analysis from here forward.
I look forward to receiving the check.
Okay. All right. Well, if you have any other thoughts, feel free to come talk to me or Dave, or email Hansi. And we'll adjourn now for, oh wait, actually, before we adjourn, for a bunch of people in the room, can I just get a quick like show of hands if you might be interested in coming to a happy hour this afternoon? Okay. And then if so, would you prefer Southern Sun or Legal Pete's, which is like Mexican food? Southern Sun is like pub food. All right, so thank you for coming back to the afternoon session of the Polar Climate Working Group. We're going to have another series of talks again, both Antarctic and Arctic focused, and then we'll end the day with a discussion. So we're going to start with Christine Shields, who is based here at NCAR.
Okay, thanks, Alice. Let me get this going. All right, so can you all hear me? Yeah, okay. All right, so this work is I'm going to talk a little bit about atmospheric rivers and their importance for the Antarctic climate. This work has had it's been a team effort. I'm definitely a lot of people involved. Michelle McLennan, who's now at the British Antarctic Survey, Jonathan Willey, who's at ETH Zurich, and Becca Bateman, she's a PhD student at CU Boulder. And just a plug for Becca, she's giving the CGD seminar in 2 days' time on Thursday, and she's going to talk about drivers of Antarctic atmospheric rivers, and gives great presentations. So if you're here or going to, I would highly recommend going to her presentation. Okay, so I have divided this talk up into 3 segments, and it's a short talk, so it's a little bit of a broad overview talk. So I'm just going to go ahead and start with definitions and mechanisms. And this is the first sort of slide on identification, and it's sort of easy to identify atmospheric rivers when you look at satellite pictures. Okay, doesn't work. Okay, see if I can do it this way. Yeah, oops. There we go. This is going to be hard using this without accidentally advancing it. So in satellite pictures, it's very easy to identify atmospheric rivers. Here, this is the one on the left is showing this beautiful atmospheric river that's crossing over the South Atlantic, and it's making impact on the Antarctic sea ice zone. And this example over here on the right was, it happened during the East Antarctic heat wave that happened a few years ago, and it brought an enormous amount of water and heat into Antarctica and really impacted temperatures and precipitation on the Antarctic ice sheet. I'm sure everyone here knows about that. But when we think about them in terms of identifying atmospheric rivers on gridded data sets like reanalysis or in models, it's a trickier problem. And so we use these things called atmospheric river detection tools. ARDTs is sort of like a acronym that we use. And for polar locations, it's really important to use ARDTs that are specific
for the poles, and in fact, using a meridionally dominant constraints to identify the atmospheric rivers, because otherwise you don't really get the atmospheric rivers detected onto the continent where you actually really care about them. So we use a meridional dominant detection tool for this work. It was developed by Jonathan and has meridional geometry, and we use a threshold that is a 98th percentile of the meridional component of integrated vapor transport, and I have the equation right here, which is just the meridional wind and the specific humidity integrated throughout the atmosphere. And we use a threshold that's relative to climatology, and that'll be important when we start talking about the future. We don't use is global ones that equally weight zonal and meridional components, because that way you sort of just get glancing blows. You get the Antarctic Peninsula, but you don't really capture those phenomena that really are on the ice shelves and ice sheet. Okay, so this is just like a really brief overview of dynamical drivers of atmospheric rivers for Antarctica. This was taken from a recent review paper that Jonathan led in Nature Reviews Earth and Environment. We sort of sketched up what was important, and the people in RE made this beautiful graphic, which I love and like to show off. So we sort of divide it into 3 different parts here. The near surface piece, you can see that the low level moisture, the airstream that's coming into the continent in conjunction with this sort of the circulation gradient, and then it hits the mountain ranges, where of course it has impact where you uplift the moisture, you cool condensed warm clouds and precipitation. But what's also really important is that mountain also has downslope winds, and so this is where you have warming. So instead of precipitation, you actually have melting in some of these AR events for the Antarctic Peninsula in particular. The mid-level is where you have your low-level jets, and the upper level is sort of you have this low-high couplet, your upper level support and the dynamics, mass continuity, and all the stuff that you usually associate with storm systems. So that sort of is your brief overview, and incidentally, Becca will be talking in detail about dynamical drivers on Thursday if you're here for the seminar. Okay, so that's all I'm really going to talk about in terms of definitions. I really sort of want to go over just the climatology and trends that we've seen for atmospheric rivers in Antarctica. So this is a climatology. We have based this on MERA, but it's consistent with the ERA 5. Becca put this beautiful plot together, and there's a couple different things here I want to highlight. One is the shades of blue shows you the AR frequency heat map, is what I like to call, where you have the most atmospheric rivers, and you see these hot spots along West Antarctica and the Antarctic Peninsula, joining Maud, and these various hot spots in East Antarctica. And this is measured in hours per year, the way she's plotted this. But there's only like a few atmospheric rivers that happen every year in Antarctica. They're relatively rare, and so this is sort of the metric or the unit that we tend to use, hours per year or days per year. The other piece I wanted to show you was just these PDFs that she's plotted around all the longitudes of Antarctica for all the different seasons. And you can see that, broadly, seasonal and regionally, they're pretty consistent across all latitudes and seasons. Where we do get minimums, which is pretty robust, is in this Ross Ice Shelf region. Okay, I think that's all I want to say about that. The other thing is trends over time, as shown in the reanalysis. This we're looking again in MERA, but as I said, it's very consistent with the ERA 5. The couple things I would like to highlight here are just, Michelle is the one that actually put this plot together, and she computed the frequencies and the trends by basin. And so broadly, we get, over time, MERA has shown that the frequencies have been increasing with the exception of a few East Arctic regions. The places that are significant have that horizontal hatching. And the places where not only frequency is increasing, but precipitation is increasing is these red outlined areas. And they sort of are co-located with these hotspot regions that I've shown you previously. All right, So the bulk of what I really wanted to show was these model simulations. And so this is CSM2, large ensemble, and this is part of Michelle's PhD work that she, she just graduated and she's now at postdoc. And this is in review at Communications, Earth and Environment. We're doing the revisions as we speak. And so this is again using the full large ensemble. And panel A shows the hotspot heat map region that is fairly consistent with MERA when you take a look at the hotspots. But to make it a little bit easier, we'll look at this in terms of bias compared to MERA. The values of the biases are relatively low, so CSM tends to do a decent job in terms of capturing when and where atmospheric rivers hit around Antarctica. The one place I'd say there is a significant bias is here in this East Antarctic region, where this is related to the bias, the circulation biases that CSM2 has. They just don't have enough atmospheric rivers that make it into this portion of Antarctica. So that's probably the biggest structural problem. All right, so now let's talk about climate change. Oh, those little gray areas are highlighting. So I'm sorry if that's distracting. Looks a little different there. So this is the future climate change. And we did this a couple different ways. The first way was just looking at the present threshold. And so what's happening here is so it's basically the SSP 370 minus historical for all the ensemble members. And here we're using the 98th percentile of present day climatology. So basically what you're seeing here is Clausius-Clapeyron. As it gets warmer, there's more moisture in the atmosphere. And so these atmospheric rivers tend to be are they atmospheric rivers or not? That's a question. They're sort of blobby, but essentially you just get massive creases everywhere. However, if you scale by Clausius-Clapeyron, this is sort of the insight here is showing you as you, the ratio, the IWV ratio of historical to RCP 8.5. And as you go into the future, you use a larger, threshold. You remove that Clausius-Clapeyron piece to it. And so you're sort of removing the thermodynamic pieces, and when you're just sort of looking at what's happening dynamically, and you can see there's less of a overarching increase in atmospheric river rather than a shift. And so this is clearly a dynamical signal here and something that we're digging into for future work. Okay. And so this is, this is the AR precipitation, which is sown rain. So this is a little bit of the impacts onto the Antarctic continent. There's a lot of panels here, so I'll try to step you through what to look at. So this top row here is the present. The future, the middle row is the future using the current climatology for your reference period. So this is work with Clausius-Clapeyron sort of baked in. And then the bottom row is when we're using that scaling factor. Now the left row is just showing you the straight up precipitation. But what I really want you to draw your eye to is sort of the middle and the right columns, where the middle column is showing you the relative contribution by basin. So she's done this calculation basin by basin. And so overall, even though more precipitation happens in the Antarctic Peninsula, relatively speaking, ARs are more important for the East Antarctic regions. And you can sort of see that where you have deeper blues. And then the right column is the relative contribution to the variability of the atmospheric rivers. And so the hatching is where there are significant. So for climate change, if you use the thermodynamically driven scaling, thermodynamically reference period for your thresholding, you get widespread increases everywhere, and precipitation, the variability is pretty big. However, if you look at it in terms of removing Clausius-Clapeyron and looking at the scaled version, there's no significant change. So the question is which one should you use? And my answer would be, it really depends on what you're after. Like if you're after an impacts related thing, you don't really care what the atmospheric river looks like, if it's a blob or is it really an atmospheric river. What you do care about is the amount of precipitation that's coming out of these systems. Then you might want to use a reference relative to today. But if you care more about the structural, the dynamics, you really should be using the scaled method. All right, so this is like sort of different mechanisms as to why, but I'm running out of time and wasn't really planning on going over that specifically. I'm just going to give you one example because you can stare at those plots for like a long time. This is just a first attempt at trying to understand mechanistically what's going on in terms of those shifts. And this is summer. It's a pretty easy to interpret season where the red hatching is where you have the decreases in atmospheric river frequency. They're sort of co-located with those broader pink areas, which is the low level wind decreases, and the blues are the increases. And so this is, she's got a lot of other stuff in here, and hopefully this paper will be out soon so you guys can look at it more deeply, but we are digging into this a little bit more deeply. Okay, so to summarize everything I've been talking about here, I hope I've convinced you that you really do need these meridional dominant tools to be able to capture atmospheric rivers appropriately for this region. Talked a little bit about the dynamics, the climatology, and trends where we showed the different hotspots around Antarctica and the seasonal and regional relative consistency across these different regions and seasons. And then the model simulations, the two different ways of looking at these changes in the future, depending on if you care about the impacts and Clausius-Clapeyron, or if you want to care more about structural differences. And I will stop there and take questions.
All right, questions for Christine in the room?
Linda, do you have any interest in looking at the precipitation partitioned into snowfall and rainfall at all?
Yeah, we've done that, and I do have an extra, I think I might have taken it out. I thought I had an extra slide. Damn it, I took it out. It showed the rain and the snow. Yeah, this is just regular precipitation, sorry. Trying to remember, it's very consistent, right? You have, and there is, of course, as you would expect, more rain in the future. But that again is definitely scaled by what you care about, impacts or dynamics, essentially. Sorry, sorry, I should have kept this.
Yeah. Thank you. Any other questions? Marika?
Would you have an interest in or have you guys looked at how it impacts the surface albedo?
No, we have not looked at that, and that's a really good question.
Kind of fun.
Yeah, absolutely. Let's talk. She's got a whole postdoc in British Antarctic Survey, and we're getting this paper out the door. But we do have other projects in the hopper, and we could try to fold that in. Yeah, I'd love to.
I feel like you hear it, or at least I've heard a lot about Greenland, like there were atmospheric rivers that caused surface melting over like all of Greenland, and
yeah,
be interesting to see.
Yeah, a lot of that's temperature driven, I think, so yeah.
But that's an impact that could
Absolutely.
Be an albedo then.
Yeah, yeah, absolutely, totally. Yeah, that's a good metric.
All right. So I think we'll move on to our next presentation, which is a virtual one by Nicole. And Nicole, if you're able to share your own screen.
Yes, I will try.
If not, I can go through if needed.
I turned that off, by the way. Thank you.
Can you see my screen here? Perfect. Okay.
Great. Go ahead.
Thank you. Hi, everyone. My name is Nicole. I'm a PhD candidate at the University of Manitoba, and I'm excited to be here sharing some work that we've been doing with the variable resolution CESM, looking at projections and physical drivers of extreme precipitation in Greenland and Baffin Bay. And this work was recently published in JGR Atmospheres, and I'd like to thank all my co-authors listed on the screen here before we get started. So it's well known that the Arctic climate is warming at a rate of up to 4 times faster than the global average. Precipitation trends, though, are less clear at a global scale, but it's becoming increasingly apparent that the Arctic is getting wetter. Observations have shown us that even a small change in mean precipitation conditions can lead to a more substantial shift in the most extreme events. In the Arctic, this is further amplified by the loss of sea ice, which allows for more local evaporation and destabilization of the lower atmosphere, further enhancing our precipitation rates. And these extreme precipitation events can have substantial impacts on things like community infrastructure and the surface mass balance of glaciers and ice caps in the Arctic, depending on their frequency and timing and phase. And we've focused in on the Baffin Bay region and surrounding land masses because of the presence of many communities and large quantities of land ice in the area. So for the remainder of this talk, there are two main questions that we're going to explore. The first is, how does extreme daily precipitation change under a high emission scenario in the Greenland and Baffin Bay region? And then, how do the processes that drive the extremes, specifically looking at extratropical cyclones and atmospheric rivers, or ARs, factor into this change? So first, we need to define what constitutes an extreme event. This table from Pendergrass 2018 shows a variety of definitions that have been used in previous studies to define extreme precipitation. And you can see that depending on the definition and location, the results can vary quite a lot. So it's important to take that into account when defining the extremes for your study. And here we've chosen the last definition, which is the top 5% of daily accumulations where at least 1 millimeter was observed. And this one was selected because it's a nice moderate definition that also removes the frequent drizzle that occurs in many parts of the Arctic in gridded data sets. And next, I'm going to give a brief overview of the variable resolution version of CESM, VRCESM, and the simulations that we'll be looking at today. So VRCESM allows for the nesting of higher resolution grids within the 1 degree global simulation. And the simulations that I'm using are on the Arctic grid, which is shown here, where the entire Arctic is downscaled to 1/4 degree. And that works out to about 28 kilometer spatial resolution over the Arctic. And I'll be using existing historical simulations of 1980 to 99 from Harrington et al. 2022, and then new VRCESM simulations of 2080 to 2099 following SSP 585 for comparison. And all of these simulations are AMIP style. So that means there's a coupled atmosphere and land component with monthly sea ice and ocean conditions prescribed from existing CESM simulations. With that, let's dig right into the results. I want to start with a little look into the historical period first and compare the native resolution CESM2 for context. So here on the top, we have the historical mean annual precipitation, and then the bottom is the extreme precipitation threshold. So how much precipitation needs to fall in one day to be considered extreme. The first column is our 1 degree CESM, followed by VRCESM. Then we have the difference, and then the last column is the difference relative to our native resolution CESM. So looking at the general patterns here, we can see that the pattern of mean annual precipitation and extreme thresholds are quite similar. Your highest values are found in southeastern Greenland, and then it generally decreases as you move northward or inland across the domain. And if we compare VRCESM with the native resolution, VRCESM really just provides refinement of the patterns that we see in CESM2, which is expected since it's a grid refinement. The largest differences, though, are found near complex topography, mostly, such as southeastern Greenland. So VRCESM can better represent the steep slopes in the area, and that means that the precipitation can't move further inland, which results in more concentrated and more intense precipitation, which in turn then increases the extreme precipitation thresholds in the area as well. And we can't dig into it too much for the sake of time, but VRCESM also aligns more closely with ERA 5. And you can read more about that in our JGR Atmospheres paper if you're interested. The DOI will be on the last slide. And now let's look at how extreme precipitation days are changing. The figures here show mean annual extreme precipitation accumulations on the top, and this is just VRCESM now. And then the bottom is the mean percent of annual precipitation that's coming from extreme precipitation days. The first column is our historical simulation, second is future, and then we have the difference and differences relative to historical values. So here we see on the top row that the extremes are increasing almost everywhere across the domain, with the largest increases being found in South Baffin Island and southwestern Greenland. There's also some strong relative increases in the northernmost areas of the domain, where historically not very much extreme precipitation was seen. On the other side, we see that southeastern Greenland is actually seeing a decrease in extreme precipitation in the future. And this is the area that historically saw the highest accumulations from extremes. And then if we look at the bottom here, with the percent of annual precipitation coming from extremes, we see kind of a similar story where the percent is increasing across the domain, except for some slight decreases in southeastern Greenland. But notably, extreme days are projected to account for an average of upwards of 30% of annual precipitation in much of Western Greenland and Baffin Island in the future. And then here we have the mean monthly accumulations from extreme precipitation days in different subregions, which are shown in the map on the left. The blue line is our historical simulation, green is future, and then the black shows ERA5 for comparison. And in general, most subregions outside of southeastern Greenland are seeing large increases during the summer months, which are highlighted in the red boxes here, and then little to no change in the winter in the dark blue boxes. And here we're defining summer as July to September and winter as January to March to align with the kind of seasonal cycle and patterns of the changes that we see here. And now that we've looked at how extreme days are changing, let's look at how those driving factors are changing. This figure here shows the annual and seasonal cyclone track densities in the historical and future simulations using the Crawford et al. 2021 Lagrangian tracking algorithm. So here we have ERA5 in the first column, followed by the historical, future, and difference panels that we saw before. And the rows represent annual, followed by winter and summer conditions. So in general, when we're thinking about the difference between the historical and future simulations, there really isn't a lot of change across the domain. Our difference panels are only showing differences where they're statistically significant at the 95% level, and you can see that not many changes are statistically significant. The most notable changes, there's a slight decrease in cyclone track density southeast of Greenland, and then there's also a small increase in the summer in northern Baffin Bay, but these are relatively modest changes. And what about ARs? Here we have the mean annual number of days that each grid cell is impacted by an AR using the Tempest Extremes algorithm with the thresholds listed on the slide here. In the historical period, it was quite rare for ARs to impact anywhere north of about 65 degrees or so, particularly over land. But there is a clear northward expansion shown in the future projections, particularly in the summer, where ARs become a lot more common across the domain, and ARs are experienced at least every year over almost everywhere in the domain. Some of the largest increases are occurring in South Baffin Island when we look at the relative differences. And finally, how do these changes then factor into extreme precipitation? The figures here show the percent of extreme precipitation days that are associated with cyclones in the first row, ARs in the second, and then the final row is those that are occurring with both a cyclone and AR present. And notably, almost all of the extreme precipitation days, historical and future, are associated with cyclones. So in panels B and C here, you can see it's almost all of them, but that also shows that there's little change in their role in the future. There's some slight reductions in northern Baffin Bay and northwestern Greenland, but overall staying pretty similar. Whereas if we look at the ARs, of course, we see that strong increase in the south. So ARs are accounting for a larger portion of our extreme precipitation days in the region, largely during the summer, as we saw in the previous figures. And then notably, almost all of the ARs that we detected are occurring with cyclones. So ARs can occur without cyclones, but here we can see there's almost no difference between these two rows, indicating that for the extreme precipitation days, if an AR is present, there's also a cyclone in this region. So to wrap it all up here, we found that unsurprisingly, extremes are increasing almost everywhere and are also accounting for a higher portion of annual precipitation in the projections across the domain. Southeastern Greenland, though, is the exception to the pattern, where we think because of the fewer cyclones that may impact the region in the future, we see that reduction in extreme precipitation. And then in general, most of our extremes in the region are cyclone associated. However, the changes, particularly during the summer, are more likely to be tied to that increase in AR activity rather than changes in the cyclone frequency. And that is all that we have here. Thank you all for your attention, and I'd be happy to take questions.
All right, are there any questions in the room or online? Christine?
Hi, thank you for that wonderful talk. Did you, within the Tempest framework, I know you can look at a lot of different things. Have you taken a look at, say, tropical to extratropical to polar transitions? And I would expect that might be increasing as well.
Yeah, that's a really good question. We haven't looked at it for the study at all. We've really just kind of looked at, like, is there an AR on the day of the extremes? But we do have the data. I think that would be a very interesting thing to look at in the future.
I look forward to that.
Anyone else? Dave?
Yeah, I have kind of a technical question. I mean, I know Adam set up the domain for you, but it seems like Greenland's like really down in the one corner of the domain, and there's this transition region of the resolution across that, you know. Does that impact the VR simulation at all? Like, do you see any weird sort of effects right there?
I don't think so. The plots that I'm using don't show the full domain. Here, this is the domain that we use. We didn't use the one that's even more high resolution just over Greenland.
Right.
So I think we haven't seen anything to suggest that there's any weird border effects for our purposes. But yeah, that is something definitely to look out for if you're getting really kind of concentrated in where you're refining the resolution.
Yeah.
Well, thank you so much, Nicole. I think this is one of the first talks I've seen with applications like this with the VR CESM. So I am excited about that too.
Thank you.
All right. We'll move on to our next speaker, who is Daniel. He's from CSU. That's on.
All right. Thanks, everyone. Yeah, I'm Daniel Hugel. I'm a PhD candidate at Colorado State University. And I'd like to thank my collaborators on this work, Elizabeth Barnes, Jim Hurl, Donica Lombardozzi, and Ariel Morrison in the Atmospheric Science and Ecosystem Science and Sustainability departments. So today I'll be talking about the influence of climate variability and forced change on Arctic greening. And Arctic greening is refers to two processes that occur in terrestrial ecosystems in the Arctic. So the first is increased productivity in existing ecosystems, and this can be seen in these, in these two images on the top right here. So this is repeat photography in the same location in the 1980s and then in 2009. And you can see that it's a grassland at both of those times. But by 2009, the grassland is much greener. It can be much more productive because of higher temperatures due to warming in the meantime. There can also be a state change in the ecosystem as plants expand northward into scenes that were previously dominated by ice and snow. So in this repeat photography on the bottom, on the right side, you can see that this is the same location separated by a couple of decades. And in those couple of decades, it's changed from being a very open environment to a forest as plants have expanded into the region. And Arctic greening is driven by anomalies in growing degree days, which is a quantity that's a measure of growing season warmth. So in this work, we analyze growing degree days in a model-based framework, and I just want to be clear that that analysis is made possible by the fact that there's this extensive existing fieldwork really tying through a lot of different lines of research, ranging from fieldwork to indigenous knowledge to remote sensing, tying this change in the ecosystem state to this environmental change in growing degree days. So we study two phenomena in relation to the growing degree days. The first are decadal anomalies in growing degree days, which produce changes in ecosystem productivity and distribution that are largely elastic. So in this time series on the right, this is from observations from a weather station in Sweden of growing degree days. And you can see that there are, on a decadal time scale, sort of times where you have more growing degree days and times when you have fewer growing degree days. And then what we call crossover occurs when the warming trend becomes dominant in your environmental state, and that can drive a sustained change in your ecosystem state. And in this time series, you can see that that occurs sometime in the late 20th century. And this is philosophically similar to the concept of like time of emergence. So we use the CESM2 large ensemble to explore future changes in growing degree days, and then use the pre-industrial control as a baseline of internal variability. And specifically, we use these two different simulations to define this concept of crossover. And the way that we define this metric is just to count in every member of the large ensemble the percent of pre-industrial samples that you exceed in a year. So you end up with a time series. This is for just one member that looks like this between the 1850 and the mid 20th century period. And what you see is that you're equally likely to either exceed or not exceed the pre-industrial. So you're around 50% on this time series. And then when you start to roll this out and look farther into the future, you see that that story changes very, very quickly, and soon you exceed the pre-industrial samples most years and then quickly all years. So with the 100 different ensemble members, you get 100 different estimates of how this occurs, and then also an estimate of the mean for across the ensemble. And a bunch of different thresholds are possible, but we just say that the best kinds of statistics is when you don't have to do any statistics at all. When the mean exceeds 80% of the pre-industrial, it's clearly emerged from that pre-industrial variability. You could choose different thresholds for that, but 80% is pretty inarguable, and that gives you a crossover time for this location in northern Quebec of about 2004, which is consistent with when the tree line began to expand rapidly in this region in field observations. So in the ensemble mean, you can get an estimate of when this crossover occurs for different ecoregions around the Arctic. And what we find is that crossover in the large ensemble has actually already occurred in most Arctic ecoregions. So we're here in 2025. All of these green and blue colors are places where that crossover is either happening now in the model or happened within the previous decades, which is consistent with the Arctic being in kind of a new state as far as the environmental conditions are concerned in this work from the perspective of the terrestrial ecosystems. So each ensemble member, as I've mentioned, also has its own crossover time, which could be earlier or later than when that occurs in the ensemble mean. And the large ensemble gives us, as I mentioned, 100 different estimates of when this occurs, 100 different pictures of how this might evolve in different under different realizations of climate variability. So for this location, which now we're looking for a site in the Brooks Range of Upper Alaska, the 10th to 90th percentile from the large ensemble spans 2011 to 2037. And what we can do is take a storyline approach to investigate how this happens in more detail. So we pick two different ensemble members, one near that 10th percentile of crossover, so an early case where that crossover in the member occurs around 2011, and then one that's late, a 90th percentile case where that crossover occurs in 2037. Yes. And because CESM is a fully coupled Earth system model, we can see what's happening in the rest of the Earth system that is associated with this early or late crossover. And what we see is that in that ensemble member where crossover happens early, that's associated with a warm North Pacific and Beaufort Sea, and kind of the opposite pattern happening when crossover is late, so a cold North Pacific and Beaufort Sea. But that's just two cases, so how much credence can we put in just those two storylines? Well, when we look at composites associated with the upper 20% of growing degree days and the lower 20% of growing degree days, again on a decadal time scale across the whole time record of the large ensemble, we see roughly the same pattern is associated with amplified or suppressed growing degree days across all the different climate states in the large ensemble. And this actually looks a lot like the pattern of sea surface temperatures associated with like the Pacific decadal variability or Pacific decadal oscillation. So the sea surface temperature patterns are stable over a large number of samples, which gives us confidence that this is a fairly robust pattern. And this kind of information could help anticipate future ecosystem change in the real world. So if you change that threshold to 100%, you can get what you intuitively understand as a no analog state. So the member enters a climate state in which it exceeds all members from the pre-industrial control and is really in a completely new climate state. And that happens farther into the future. So this is generally starting to emerge in mid to late century. So whereas the climate state has already entered in a new regime, these sorts of no analog states take longer to emerge. So with that, just in summary, on average, most Arctic ecoregions have already entered a climate regime that is dominated by the warming trend. The storyline approach can illustrate plausible cases of how coupled climate variability can modify the timing of that in any individual realization. And analysis of the full ensemble provides statistical confidence in those storylines. No analog states emerge in the mid to late 21st century. And the general approach that we have here, where you can take these well-defined climate conditions that have been seen to modify the ecosystems from fieldwork, and then use that to motivate model-based analysis, could be widely applicable to a range of other ecosystems. And with that, I'm happy to take any questions.
All right, do we have questions in the room or online? Rika, I saw your hand first.
So thanks for a really nice talk. It's really interesting. So the CSM2 large ensemble, the first 50 and second 50 members have slightly different forcing, and that difference in forcing has an impact in the Arctic in particular. Have you looked at whether you have different statistical properties for the first 50 versus second 50 members?
Yeah, so we haven't. I've kind of segregated that by looking at the ones with the different biomass burning emissions. It's definitely something that's, on the, this project has been difficult to know when to stop with the analysis of the different members and the different scenarios and different other things. That's something that definitely, I think would be worth looking at in the future, but not something we've looked at now. Yeah. Just kind of qualitatively, I've noticed when I've done these storylines that we're getting cases from both sets of realization. So I'm guessing that it's not as simple as like the 50 biomass burning members cross over early, the 50 CMIP6 members cross over early, the 50 smooth ones don't. But yeah, that's just totally qualitative. Yeah.
Other questions? Yes, John.
Can you hear me?
Yes.
Yeah, thanks for the great talk. My question is about the vegetation in the model. Do you see greening in the model?
So we actually can't look at the vegetation directly. So the plant functional types they're dynamic, but they're not interactive. So the plant functional types evolve, but only as prescribed by a time series. So that's why we look at the growing degree days here, because you can't look at the ecosystem change directly in the model. And here we're kind of trying to get at this from an oblique angle by looking at how the environmental drivers evolve without getting into the question of how the land surface change is represented.
Just quickly follow up. I think the vegetation type is fixed, but the phenology is interactive.
But what is interactive, John?
The vegetation phenology.
Phenology, got it. Okay.
Gotcha. Yeah, I'll look into that in more detail. Thanks.
Thanks.
All right. Let's go ahead and move on to the next talk. Thank you so much. So I think the overhead mics are still on, so I've just given up on that.
that is hosting me here, and also Dave Kelly that helped me a lot with simulation. So yeah, I'm gonna talk to you about rapid Arctic sea ice loss events. So I don't think I have to introduce you Arctic sea ice extent. We all know that September. Oh, should I do some? Oh, it fell down. Okay. Yeah, I don't know. Okay. Arctic sea ice extent, September Arctic sea ice extent is shrinking, and the state of the Arctic looks very different now that it used to be. And a climate model suggests that the future Arctic sea ice decline will be erratic rather than smooth. And that will lead to fluctuation to subdecadal to decadal timescale with rapid decline followed by relative stability. And here we are studying these fluctuations through the lens of rapid ice loss events that are reduction in sea ice extent that occur at a much faster rate than expected from the forced contribution. And we study these events with a definition from Auclair and Tremblay from 2018. So for example, in this figure, you have September Arctic sea ice extent trajectories from CSM2 less melt. So we talked a bit about CSM2 less melt is a tuning of CSM2 that incorporates a specific parameter aimed at reducing sea ice melt. So the definition, when we apply the definition, what we do is that first, if we isolate one of these members, we first apply a 5-year running mean to filter out the interannual variability. And then we looked at linear trends that have a trend that exceed a certain threshold of 300,000 square kilometers per year for at least 4 consecutive years. And in this particular member, we have 3 of those events. And these rise will become the rule rather than the exception, according to CMIP6 models. So here what you can see is the total number of rise in a multimodal ensemble of 26 models with 2 different scenarios, a low emission scenario, SSP 1, 2.6, and a high emission scenario, SSP 5, 8.5. And at the beginning of the year, the forcing is really playing a role with a lower amount of RILE from January to July and a higher number of RILE for the higher emission scenario. But in the summer season, the number of RILE is consistent across the 2 scenarios and is up to 50 RILE for this multimodal ensemble. So an average of 2 RILE per simulation. If we looked more timely at the percentage of simulation with at least 1 RILE before 2030, we see that it's quite low for the 6 first months, but then it increased during the summer season with 70% of these models having at least 1 RILE before 2030 in the summer season, and regardless of the chosen scenario. So now that we know that these rise are a common feature in CMIP6 models, the drivers still are uncertain. Some studies point the oceanic processes, the atmospheric processes, radiative, non-radiative. It's a bit all over the place, so there's a lot of still to understand in this topic. And another thing that is uncertain is if there are mechanisms of sea ice predictability for rise in the Arctic. Some studies suggest little to no predictability due to the increasing variability associated with the thinning ice cover, while other studies show some predictability due to large-scale control by atmospheric circulation or perfect model with potential predictability up to 3 years. So that question led us to want to perform a sensitivity simulation with CSM2 less melt. So what we did is that we look at rise in CSM2 less melt members, and we isolate one RILE for which we have restarts in the onset of the RILE. So that will help us to investigate if there is key factor like internal variability, initial sea ice condition, external forcing, ocean sea ice condition too. So this is the RILE we chose that start in 2050 that has a mean state around 4 million square kilometer, and in 6 to 7 years, it dropped to 1 million square kilometer. So first, we looked at the internal variability, and to assess the role of internal variability, we only introduced perturbation on the year of the onset of the RILE, so January 1st, 2050, and we applied small rounding level change to air temperature. And because of the chaotic nature of the system, all of these simulations diverge. And then to this sixth simulation that you can see here in green, we apply the definition of RILE. And what we observe is that every one of these simulations show a RILE in September. So that means that here internal variability looks like it doesn't play a dominant role, or there is something more to it. So after that, we were interested in initial sea ice condition. And what we did to assess the initial states is that we change the sea ice states at the onset of the RILE, so in 2050, with 3 different initial sea ice extent initial states. So we chose a year with a similar sea ice extent, sea ice volume states, which was a year with a higher sea ice extent initial state, and a year with a lower sea ice extent initial state. And we apply the definition again, and here in 85% of the simulation, a RILE still occur in September. The 2 no RILE that you can see highlighted in yellow are simulations that were initialized with a lower sea ice state. And what we observe is that the sea ice increase and then stabilize, and that prevents a RILE. And it's true that in this simulation in 2050, compared to other members of CSM2 less melt, the sea ice state is a bit higher. So we wanted to test last the external forcing because it seems that a lot of this simulation end up showing a rise. So maybe the forcing in 2050 is quite strong. So what we did here is that we switched the scenario at 2050 to a lower emission scenario, the SSP 1.2.6. So going from SSP 370 to 1.2.6. And we also did it with a higher initial state. And what we observe is that the majority of this simulation still exhibits a RILE in September. So at first we were, and a reason is that SSP 1.2.6 scenario in the forcing can still be quite strong in 2050. It starts to decrease after 2050, but it's kind of similar to 3.70. So at first we were really excited to have RILEs, and at the end we were quite upset that everything that we do, we end up with RILEs. So we were like, maybe it's not the good one, maybe we should turn to another one earlier in the century. So this one started in 2020, and around 6 million square kilometer, and drops to 4 million square kilometer in 2025. And as the first simulation, we just introduced a perturbation on January 1st. And we chose 2020 because at that time, the forcing should remain quite similar to the external forcing we observe today. So we ran these simulation that you can see in all colors here. And indeed here, we don't end up with a rile every time. There is only 2 simulations that show a rile in September, so internal variability looks like it's more dominant. But we can see that the S4 and S5 quite approach the threshold of rile. So the negative number you can see is the trends, the linear trends, and the threshold is minus 0.3. So not a rile, but quite close. So the conclusion here is that by 2050, the forcing, regardless of the chosen future scenario, could be strong enough to drive CRs towards a rile, irrespective of the initial state or ocean state. We also did the analysis with the ocean states and end up with rise. Or maybe the mean state of the September CR extent in this particular member is significantly higher, and could explain that the majority of the simulation with its short rile. So that's very preliminary work. We need to assess all the data, and we want to assess the sea ice mass budget in the future to look whether these events are driven by an excess of melt or deficit or growth, or investigating the mechanisms, do composite analysis to look at air temperature anomalies, heat content, and other potential contributors. Thank you.
All right, questions for Annalise?
So I was sorry if you said it. I was just curious, when you did the perturbation experiment of the sea ice conditions, were you just changing the extent or also the thickness of the ice?
So just we changed the whole component of the ice.
Okay.
Anyone else online? The room?
Have you looked into whether the initial conditions or the CS conditions when at the onset of one of those rapid CS lows is usually like higher than you would expect, or higher than the, let's say, ensemble mean? Because it kind of could be kind of like a regression to the mean, in which for whatever reason internal variability you have a higher CS extent than the equilibrium, and then it naturally will go down. So then whatever you do to the sea ice or to the atmosphere, it should relatively go back to the equilibrium.
So what if we look at the sea ice?
So if at the onset of those rapid events, do you usually get kind of like a positive anomaly of sea ice extent compared with the ensemble mean?
Okay, yeah. I have not looked at that, but that could be interesting. Yeah, in this particular member, the anomalies is clearly positive compared to the mean.
Yeah, but others might have like regular.
Yeah.
I had a quick question. So your 2050 initialization, you changed the forcing to SSP 1.26, and then you said, but it's still kind of similar to the 3. Whatever. Do you know if there's like a negative emissions scenario, like from the HOPE experiments or something like that you could try and set that is significantly different in 2050?
Yeah, no, I don't know if there is. It would be interesting to have that, or maybe the historical.
Or something.
Yeah, we tried with the SSP 1.19, but it wasn't working. Yeah. So yeah, it would be interesting to see if we can even remove the extended filtering.
All right, thank you very much. Our final science talk of the day will be by Chloe, president from CSU. Yes. It's a slide down. Yeah. I'm a graduate student at Colorado State, and this is work I've been doing with my advisor, Dave Thompson, and then also in collaboration with Ed Blanchard-Wigglesworth, who's at the University of Washington. So generally this work, we've been looking at understanding kind of the role of the atmospheric circulation in some of these recent Antarctic sea ice anomalies. We specifically for this work focused on the role of the Southern Annular Mode. So cool. So, oh, I just get really loud, but okay. So I'm sure all of you are well aware of the recent trends in Antarctic sea ice, but here's a time series of Antarctic sea ice area anomalies across the satellite period. So you can see the positive trend up until about 2015 and then the rapid loss since then. On the left is showing just the seasonal cycle of Antarctic sea ice, which has a very large seasonal cycle in the Antarctic, especially compared to the Arctic, with your annual minimum occurring in February and then your annual maximum occurring in September. And there's been a lot of work done trying to understand what the physical mechanisms and the reasons behind a lot of this recent change has been, with work done on looking at increases in upper ocean heat content, teleconnections to tropical climate variability, atmospheric anomalies such as zonal wave number 3 pattern and the SAM. So today, as I mentioned, we're going to be specifically looking at what the role of the SAM is in recent sea ice anomalies. And as I mentioned, there's been previous work done on this, but a lot of the previous work has been focused primarily on the SAM during the austral summer season. And we were interested in taking more of a seasonal approach by looking at how the linkages might change as a function of season and then also as a function of lag. And so I'm going to start by showing some work done mainly with reanalysis and satellite data, but then we also looked at linkages in CESM2. So there'll be a little bit of both in this. So for at least our observationally constrained data, we used sea ice data from the NSIDC, wind and temperature data from AIR5, and then the SAM index from the NOAA CPC. We used a mixture of sea ice extent and sea ice area and sea ice concentration. Sea ice area is just computed by multiplying the sea ice concentration data by the grid box area and then summing it across the southern hemisphere. So first, as I mentioned, so we were interested in not looking at the austral summer to start with, just because that had been a little more well researched. So we first started looking at what is the relationship between the SAM in September and sea ice. So if we look at, so each of these 4 plots here are different months of sea ice regressed onto just the September SAM. So if we start in panel A, the vectors there are the September near surface winds also regressed onto the September SAM. And so you can see that the pattern is dominated by increasing westerlies, as you would expect with a positive SAM anomaly. But there's some interesting areas where you're getting more poleward or equatorward wind anomalies. And those are overlaid, so the coloring and shading is then the September sea ice anomalies regressed onto the September SAM. And you can see that those areas where there's more kind of meridional winds, you're getting these either positive or negative sea ice anomalies occurring. And then if we look at kind of increasing lags as we look at panels B, C, and D, so those are different months of sea ice, all regress just onto the previous September SAM. You see that these positive sea ice anomalies persist and they move as the ice pack contracts into the Gehedi as you head into the summer. But generally, you're getting these positive sea ice anomalies resulting from a positive polarity of the September SAM. And so this is kind of the spatial pattern. We can take an area average of this pattern and look at, and that will tell you basically what's the sea ice area regressed onto the September SAM. And that's what's shown in this row here. So this is just sea ice from different months at different lags, all regressed onto the September SAM. This is looking specifically at sea ice area versus sea ice concentration, which was the pattern we were looking at before. And this kind of allows us to take a quicker look at just what the sign of the relationship is between sea ice and the SAM for this particular month, September, and then we can extend this to the rest of the months during the year. And so this figure here, each row is a different month of SAM that we're regressing sea ice onto. So the September row there is the row we were just looking at. So it's just showing that negative relationship where you're getting positive SAM anomalies resulting in
negative sea ice anomalies. And then so on the x-axis, that's your function of lag. That's your different months of sea ice you're regressing onto the particular month of SAM. And so I think there's a kind of a pretty distinctive pattern that pops out here. There's kind of two relationships. There's a relationship during the sea ice minimum season, which is a positive relationship where given a positive polarity of the SAM, you'd expect positive sea ice anomalies. And then there's a different relationship during the sea ice maximum season, where it's a negative relationship, where again, positive SAM, you're getting negative sea ice anomalies. And this kind of seasonal cycle of the sea ice is shown on the right, just kind of for reference to highlight, again, the seasonality of the relationship. And so to dig a little more into the sea ice maximum season, and I guess, let me go back. So one thing I didn't point out is that it's quite distinctive that the relationship during the sea ice maximum season is very persistent. So the relationship during the sea ice minimum season, you're getting sea ice anomalies for maybe 3 or 4 months after an anomaly in the SAM. But during the sea ice maximum season, you're getting sea ice anomalies that are that extend for the following year. And so we were interested in kind of understanding what drives this persistence of this relationship, particularly in the sea ice maximum season. So we started by looking at what the shortwave fluxes are doing in response to an anomaly in the SAM. So the very top row you've already seen before, that's the sea ice anomalies onto the September SAM. But then the middle row is clear sky shortwave fluxes regressed onto the September SAM at those designated months. And then the bottom row is the shortwave cloud radiative effect regressed onto the September SAM at those particular months. So what I want to draw your attention to is that in particular in the middle row, you're getting positive anomalies, increased shortwave fluxes into the surface that are co-located with those areas where you're getting negative sea ice anomalies. This of course makes sense because especially as you're heading into the summer season, as you're melting the sea ice, you're opening up the darker ocean and naturally you'd get increased shortwave flux. This is slightly offset by an increase or an outgoing kind of shortwave or an increase in shortwave cloud radiative effect. So you're getting a little more clouds over those open ocean areas. This is consistent with previous work that's shown kind of this open waters resulting in more low level clouds. But I think what's most important and most dominant is this increase in clear sky shortwave flux into the surface. And so this provides kind of increased heat and energy into the ocean. And what I'm not going to show here for sake of time, but we showed that you're getting then warmer SSTs that are able to persist this low sea ice state through the rest of the year, even as you head into the following winter and you lose kind of the effect of the shortwave fluxes. And so as I mentioned, so this all previously was done with reanalysis and satellite data. And so we wanted to see if these linkages were also present in models. And so we looked at CESM2 historical simulations. We just have started out by looking at just the 11-member CESM2 historicals. And so this is the 11-member ensemble mean. This is the same sort of plot that we looked at before with the observational data. And what I think is quite noticeable is that the same seasonality of the linkages between the SAM and sea ice are very present in CESM2. The amplitude's a little bit smaller, and there's a little bit of differences, especially in the sea ice maximum season of which months are popping out and exactly what the relationship is like. But for the ensemble mean, there's this distinct seasonality is still quite clear. And then if we look at, we were also interested in looking at kind of future projections or like future simulations and how these linkages might change. And so what we did is we took the common ensemble members between the CESM2 historical simulations and then SSP 585, and we kind of then created this record that lasted from 1900 until 2100. And then we broke that record up into 50-year chunks and then created again these kind of regression matrices of sea ice area regressed onto the SAM for each of those different chunks. And so that kind of allows you to look at how these linkages might change as the sea ice is melting, as your general globe is warming. So you can see that the relationship is quite similar up until about 2000. And then as you get further and later into the 21st century, your relationship starts to fall apart and kind of become a little less clear. I think this kind of makes sense because that's also, of course, when you're melting a lot of the sea ice. If you don't have the sea ice to have these linkages, it's going to be a little less clear. But I think it's interesting that you can see this even in just these, even in just this one model in CSM and It's quite, yeah, it's encouraging to see that this relationship is present in CSM like it is in the observational data. And it kind of opens the door, I think, for different ways to kind of investigate these interesting linkages. And so just to wrap up, so this work has been showing that changes in the SAM kind of impact sea ice during two kind of distinct seasons, and there's a distinct seasonality of the relationship. There's a positive relationship during the sea ice minimum season and a negative relationship during the sea ice maximum season. The persistence of sea ice anomalies during the sea ice maximum season has the ability, has a distinct impact on actually the annual mean changes in sea ice area. And so something I didn't show is that if you regress annual mean sea ice area onto the different months of the SAM, especially in September, the September SAM has a marked impact on actually the annual mean sea ice area, not just the couple months following. And then finally, as I showed, these linkages are not just present in some in the recent observational data, but also reproducible in CESM too. So yeah, happy to take any questions.
Can you run this on CSM3 like tomorrow? I mean, well, no, seriously, like how long does this analysis take you generally?
To do, I mean, given that, not very long. Yeah,
Okay.
not super long. And I mean, this is of course just using output, and I didn't like run CSM2 with different, this is just using the historical simulations, of course, which really available. So, but yeah, actually doing this, creating these sorts of plots, not that long.
And if we have data, then you could,
Yes.
in theory, run it on that pretty easily.
Absolutely, yes.
Okay. It's good to know.
Yes.
Do you have copious spare time?
Yes. You have some, yeah.
Amazing.
Yeah.
All right. Are there any other questions? Christine?
You probably haven't done this, but how robust is this across models, do you think? Do you think it would be different models, different responses, or?
Yeah, I haven't done that. That's something I'm very interested in doing. I think that's be a really good thing. My gut would say that as long as the model has a pretty good representation of Antarctic sea ice, I would think it would be pretty robust. I think that there's clearly, depending on like what the SAM variability also looks like, I think that's why like September pops out more in the reanalysis and observation, because it's had more recent variability than in like the CESM2 simulations we were using. So I think that also would, depending on what that looks like in the model, it would like maybe vary a little bit, but based on how well it was reproduced in CSM, I would think that it would, yeah, be reproduced in most other models.
Elio?
Yeah, so you started talking about the trends or the recent decrease in sea ice. So how does this connect to that? Because the Southern Island more so has a trend, but it's mostly in summer, and that's not a lot of relationship there. Summer more September when there's no trend. So how does it relate to that?
Yeah, so I should have put this as a backup. I have a figure that we looked at, basically if you look at the time series of like the September SAM recently, and then look at time series of different months of sea ice, you see that there's been some really big variations in the SAM in September. Like there was a really big negative anomaly back in 2014, 2015, and then really big positive anomalies, and they track very well with some of these recent sea ice anomalies. And so I think in the past decade especially, there seems to be like this kind of more clear visual correlation between the two that I think kind of indicates that these really big variations in the September SAM recently especially have like kind of helped promote some of these recent sea ice anomalies that we've had. So yeah, I can show you the figure after if you want, yeah.
Are there any questions online? All right, Julie?
Yeah, really interesting. So I guess following on from that, do you think, I don't know, the late or the spring kind of SAM is more closely linked to La Nina and El Nino than other months? So is there any hypothesis of why?
Yeah, we haven't directly thought, or yeah, something we've been thinking about. We haven't really looked too much at what maybe the connection would be to El Nino. So yeah, that's something that I think we're still thinking about. Haven't like directly necessarily looked too much into yet, but that's a really good point and question, and yeah, something to think about. Yeah.
All right, well, let's thank all the speakers again. So
So I think at this point, we have a break for 30 minutes.
All right. So we're back here for the Polar Climate Working Group, the final discussion for this winter working group meeting. So the theme and topic of today's afternoon discussion is future plans kind of beyond CESM 3, not only exclusively. So the first thing I just wanted to update everyone about, and this is partly because people have asked me about computer hours and stuff. So we had 22 million core hours allocated in this cycle, and we've used about 8.6 million of those. So we have 13.3 million hours left. And I know some people have requested hours, there are many people who requested hours who have not been charging at all. So if you have done that and you are at this meeting virtually or whatever, then please use them. But if you're not going to use them, also let us know, because there are people, students and others in this room who are itching to use more core hours. The other thing I wanted to point out, just if anyone is familiar with this, is that the allocations used to be 2 years. This allocation is 18 months, so it's going to end at the end of next April. And this is just a little weird, but we're trying to shift when our allocations end to not correspond to a different allocation anyway. So there'll be another call for resources near the end of that allocation. So there's often a chance to ask for more, but I just wanted to emphasize that we have some of these and you should ask about them if you're interested. I also wanted to have some conversation here before we go into CESM 3+, about possible community projects that people might be interested in using some of our allocation hours for, or other things that you think might be important. So I think if I stop using this, because I'm going to take notes, the roof mics are still on. But the couple things I just want to point out, I mentioned this morning, there is no current plans that we are aware of for a CESM 3 large ensemble. Last time with the CESM 2 large ensemble, we collaborated with folks in South Korea, and it was actually run there. And then now we have the data here, but we don't have that same sort of collaboration going on. And so there has been some discussion in working groups about, each working group contributing some resources to putting together some maybe medium ensemble. I don't know exactly what that would be, but I wanted to at least bring that up and we can talk about that. One thing that's come up in this meeting repeatedly is the interest in nudging. And so I wasn't sure if there's any interest in would it be beneficial to the community to have some sort of nudged experiments that are community experiments, maybe in CESM 1, CESM 2, and CESM 3, using the same nudging. I think there's a lot of questions about this. Do we nudge globally? Do we nudge both hemispheres, but only from say 40 respectively towards the poles? I don't know. I think there's some things that we'd have to detail, but lots of people are interested in using these nudging experiments, and maybe in some cases they'd be useful for comparing more directly to mosaic observations or something like that. So, or looking at recent extremes, that sort of thing. So I wanted to bring that up. And then I feel like maybe I've brought up other things in the past, but I can't remember them right now. So I just put others as an unknown here. So maybe let's talk about this for about the first, I think we have an hour allocated for this discussion. So maybe we can talk about this for the first 15, 20 minutes, see how this is going, and then we'll talk about potential future plans. And then it can be kind of open mic for anything else that we need to talk about before we wrap up, and anyone who wants to join can come to Southern Sun. So would you guys mind putting the pictures up, and then I'll go back to the presentation after this 15, 20 minutes, and that way anyone can join. And we do have at least, so anyone who's virtual, if you want to turn on your cameras and be part of the conversation, we know you're there, so we can see Hansi and Cece. And I guess before we start, Hansi, if there's anything else you want to add that I started this conversation with, please feel free to jump in.
All right. Thoughts, CESM 3 large ensemble, medium ensemble, whatever that is.
Yeah. So what's the current plan, just as part of CMIP 7, I assume? Will it be 3 ensemble members, or what kind of the standard that is planned?
I don't know
I
what the.
have
sample
not
is.
heard yet. Yeah.
Like more than one would, I think, be very important.
Yes, yeah.
The number we can talk about, but like just one run
Yeah.
is very sad.
Yeah. Well, so to qualify, the historical runs, we did 10 or so,
Yeah.
but each of the scenarios, we only
Three.
three
Yeah.
for each of those. I can imagine it would be somewhat similar. But again, we're still sort of just waiting on the official forcing.
I think even if this group has a recommendation for a minimum number of
Yeah,
ensembles, that
yeah.
would be
Yeah.
useful.
Yep.
So.
In terms of the minimum, do you know, Claire, it's based on, is Adam here? No, based on Claire's work, she has, I think, a paper or more on like,
Yeah.
you know, minimum number of ensembles for looking at blah. So maybe,
Alex has done that kind of work
Yeah,
for
okay.
CIs.
Yeah.
So.
yeah, back then for CS, it was like 12 where like it starts to flatten off. It's still useful to have more, but like you get a lot of
Yeah.
increase in spread up to
Yeah.
12. So there you go, 12 minimum. 10, 12.
I know, yeah.
Might as well say 12. Yeah. Always start high, right? I'm not saying negotiate.
Well,
Give 15.
Yeah, I think with the future stuff, it's sort of hard because, you know, you're trying to address ensemble and scenario uncertainty, model uncertainty, you know, all these things. And so, yeah.
And I will be, there is some like task force for the CESM3 CMIP 17 that's looking at the forcing, but the rest of us haven't really, like, we're not running CESM through with it yet. I think Julie said earlier today, it was just finalized like last week, minus a couple things. And at least for CESM2, we found there were lots of challenges with it. And so I'll add that in a second. Yeah, thanks.
Oh, polar amplification.
So
Yeah.
so I think, you know, we're not super familiar with it and we don't even know what the model looks like with it.
Right.
But I think, you know, when I was saying like, maybe people will pool and have like a medium ensemble, I mean, like the CSM2 large ensemble was 100 experiments, though it's kind of two groups of 50. So a lot of people just look at 50. And so I think knowing what's, you know, do we want to have 20, 30, 40, you know, 40, like what's the, at what point do we get benefit, but it's not going to be unreasonably expensive, I think. So that's a good option. And as you guys probably saw, CC put up there that for polar amplification work, it benefits to have like 20 ensemble members. So Alex said 12, I said 15, CC is raising it to 20. So I think that's good. Keep it, yeah.
Yeah, if you need another motivation for a larger ensemble, we have a tool now in Dart, which we could possibly implement with CESM, which allows us to use a climatology of the model to reduce the cost of the assimilation by a fairly large factor, like 50 or 75%.
Okay.
So that could make it more accessible to a lot of projects. It's just one more data point there.
I guess the other thing would be which scenario. I haven't actually paid attention, so I don't know what they're gonna be called for CMIP 7. Probably something different than last time because they always change it, but like last time, like it was the 370. The first large ensemble was 585, and so kind of which because if we do 20, probably can't do it for all 4 or 3 or
Right.
whatever that the CSM3 is going to be run for
Right.
in the future for like
Right.
Dave said for the historical. That's easier.
Yeah.
Than ones that branches.
I think a lot of that was hindsight too, you know, because we did do the RCP 8.5 for the CSM1 ensemble. And then our intention was to sort of do 585, you know, because it would be analogous, but then it turned out to be way stronger than we imagined. And so we backed off to the 370 for the large ensemble. So,
I think
Yeah.
it was part of the CMIP 6 protocol that 370 was like, if you had multiple members, do it for that one. I remember reading that in the protocol.
oh, was that there too? Yeah, okay.
Will a medium LE be with the fast track model? You know what, I doubt it. So the fast track, they're trying to get a fast track model to run soon for CESM or for CMIP 7. And ideally that would be CESM 3. but there might be developments beyond that. I would actually advocate that we don't want a medium ensemble with unless we feel like the model is really ready. I don't want to rush a medium ensemble with something that's not ready. Like we were talking about the Southern Hemisphere bias. I don't think there's a point in my mind of having 20 ensembles, but the sea ice looks bad.
Another technicality that might be of interest here too is we're not going to have this confusing thing where we have the CSM2 CAM and the CSM2 WACM things this time around. They have sort of agreed on instead this sort of compromise top. And so there will only be one CSM2 sort of set of experiments out of that. And it's, we hope with this mid-top, but we haven't really done a lot of runs with the mid-top at this point. So just another thing. So
I was talking to Isla earlier and she said that it doesn't look like there's huge differences.
Yeah.
The same way.
Yeah.
So.
yeah, that's right. Daniel.
Is that the same as the middle, is that the middle atmosphere configuration of WACM, or is this like a completely different,
Actually, I don't really know the answer
Okay.
to that, but I'll, you know, I can definitely put you in touch with the people who do know. Yeah, David.
I was wondering what the plan, maybe you went over this earlier, but what the planned forcing is. Like, are you thinking that you run CSM3 with the CMIP6 forcing?
Yeah, we discussed that also. So last time that wasn't part of the protocol, and Isla said that this time for I'm forgetting what it was called, but it was like hang on.
PA MIP, I think she said. Anyway, one of the MIPs.
PA MIP. I don't think
Yeah,
that means
yeah,
data
yeah,
assimilation. I don't
DA
know what it
yeah.
means. That having like the new model with CMIP6 forcing as part of the protocol so that you can better get that like forcing versus model difference. If that wasn't going to be something we did, I would also advocate for that so that we understand. I think that was valuable. The one that Polar Climate Working Group, led a lot of last time to be able to understand what's the forcing versus model difference in everything we're seeing. Otherwise, you're just kind of like, oh, it's different. Okay. So I will add that I think I'm seeing lots of nodding that there's interest in making sure there's a CESM3 with CMIP6 set of experiments available. Yep.
I think another thing for people to be aware of it is that the plan is to have an emissions driven model. So,
Yes.
emissions of carbon and the full carbon cycle computing the atmospheric CO2 concentrations as opposed to prescribing atmospheric CO2 concentrations. So it's just a difference in, that's the plan or that's the hope. We haven't actually done
We haven't done
those
that with
simulations yet. So
CSM3 yet.
if our carbon cycle gives us,
Yeah,
twice the amount of atmospheric CO2 than it should, maybe
yeah.
that will change, but that's the current plan.
We did do this with CSM2. We had the ESM configuration. I think we only had one run in that configuration where it was emissions driven. So,
So I think that's another question perhaps is,
Yeah.
is it important to people to have a non-emission driven run to compare back to previous model versions where the CO2 concentrations are prescribed?
And if there's a CMIP6 force one, that probably would be that, or would that also then be emission? Because like, probably just for comparison purposes,
Mm,
probably should be
yeah, yeah.
prescribed
Yeah.
forcing rather than emissions for the one that Dave was saying, like the CMIP3 was CMIP6 forcing. That probably would be a forcing, not emission driven one.
Well, we could do either. And,
Okay.
we've done both for CESM2. It's just
Yeah.
the large ensemble, of course, is a prescribed CO2.
right.
So we only have one or, I don't know, a small number at least of the emission driven simulations for CESM2.
So just to summarize, so far, I'm hearing that people are interested in a large ensemble or a medium ensemble, whatever we'll call it. I think some details of that have yet to be worked out, like whether it's emissions driven or prescribed forcing, and then that it might not be the same version of the model I think it looked like people were nodding when it's like, it'd be better to have a model that we're really happy with than maybe the fast track model for that. And then the second thing is that people are interested in this set of model experiments of a model with different types of forcing so we can better attribute the changes we're seeing. And I think, like you said, there's still a lot of unknowns with what's going on.
Yeah, Alex.
Yeah, and I think having a nudge simulation would be really helpful too, because we're kind of like looking at.
Great minds think of.
Yeah, just kind of compare, because otherwise people do them individually, but then they're not located, like everybody can access them. And so that would be, I think, a great resource. And yeah, then we probably should talk a bit more in detail, like how they should be nudged. And but I think that would be a great community project.
Would there be value in doing that for CESM2 and CESM3? Or maybe seeing if some of the people that have done CESM2 runs would be willing to share them, and then we make sure the protocol is the same in terms of how the nudging is applied, or.
Yeah, because like sometimes when you run it yourself, it's on your own campaign, and then other people can't easily access them. And so it's always, so if we could kind of get some of that output onto like the Polar Climate Working Group storage or something, that would be great. Yeah.
We were talking about this at lunch also. But I think, along the lines of what Tsinghua was talking about and what Ash brought up as well is, it seems like maybe nudging has changed a little bit, like something in the model has made it a little different between 1 and 2. And so I do think, especially if people already have some of the nudged experiments for CESM 1 or 2 available, and then you put some resources towards 3, and we can sort of intercompare those as well, that might be valuable for like what Tsinghua was mentioning about trying to understand what's happening with nudging. Yeah.
Additionally, I know like Will Chapman is working on another version of the nudging physics. Last I tested that was worse. I don't know how it has evolved since last fall, but I don't know if that will be the version that's included. Oh, okay. Yeah.
Let Cece turn too. Yeah, you can also unmute Cece.
Yeah, I'm happy to. We definitely had surprises when we started using his method. But if you look at what he did, it's very smart. And then when, so we think we probably had other compensating errors in when we weren't using his method. But now that we are, you can actually just verify that the root mean square, your departure of the target wind and the simulated wind with nudging. So the nudging is to the target, so it should be the same. The root mean square error goes way down. That's good, right? You're basically getting a lot closer to the target with his method. So I can't say, objectively, it looks like it's really the right thing to do.
I think it'd be nice if because there's multiple people with experience in using the nudging in different model versions, and it would be nice if those people might contribute to figuring out an experimental design for CESM3 runs, like CC and Tsinghua and Ash and Ed and Letty, and there's probably others that have been.
Zach Espinosa.
Yeah.
Zach, yeah, so maybe we could Alice could reach out to the whole working group, but maybe seems like there's an obvious subgroup of people who've already been doing these runs
Does that
that can provide guidance.
Does that mean we should call it nudge MIP?
Are there
Hi,
any?
this is Alec. I was just wondering about time periods. If compute is an issue and you're trying to generate more ensembles, is there conversations about kind of shorter runs or anything like that? I know it's probably hard to do that and keep things consistent, maybe. But...
I guess I'm not sure I understand what you're asking. I don't
know if there's ever any conversation about running shorter time period simulations, but with more ensemble members. Or if that ever makes any sense. I know obviously ideally we would just have it for the full record, but
Go ahead.
I mean, like with the CSM1 large ensemble, you know, we started in 1920 instead of 1850. So we just cut off the first 70 years
right,
in part so we could have more ensemble members.
right.
So I mean, we still had from 1920 to 2100 in that case, but I mean, I think we could make those kind of compromises.
Mm-hmm.
Shorter record and more members, and then it's, you know, when do you start?
Right.
Yeah.
Do you have to go to 2100? Is 2050? And you know, those, but
Yeah.
I think we could provide guidance on those questions too.
I think one thing we might want to do for this, and like Annalise ran into this to some degree with, this wasn't the large ensemble, but you don't always have restart files at convenient, useful times. So make sure that we have restart files, whether it's every 5 years or 10 years or something, so that maybe it's, you know, maybe Alec, like if you're specifically interested in the 2050s, you could run several that are just 2 years long in the 2050s, something like that. But we know we have a restart file that you can use to do those, or maybe we do that too. I think it's just, it's hard to know what for different applications, it's like different decades that are of interest, you know, so it's hard to decide which ones. I think, you know, I'm not like, oh, the 2050s are the most important because of X. So
Yeah.
Have we heard about like another decadal prediction ensemble and that sort of thing? And that was something they did too, and the shorter runs. So.
So these are the ones that we brought up. Are there any other experiments that we haven't talked about or brought up that people would be interested in doing, either as community projects or something like that? David?
A non-nudging related one, but I'd be particularly interested in the coupled models sensitivity to observationally uncertain parameters. I think about basically how much work was spawned by the Urego Blanco et al. Paper within the observational community that, hey, here is a roadmap of uncertain sea ice parameters to go improve observations, but obviously as a standalone sea ice model, and the answers may be different in a coupled model, maybe different in a new generation of the model.
Okay. I guess a couple other things just to let everyone in the working group be aware of is, I think last week at the Ocean Model Working Group, there's a team that's putting together a package to do regional configurations that's called Crocodile, which I don't know what that stands for, but they have a pretty good, it seems like they're making a lot of progress with setting up the regional ocean domains. There's some questions outstanding about how and if sea ice can be part of that. So there might be like a regional Arctic domain that would be all of the Arctic, so that we don't have to worry about boundary conditions of sea ice to be determined, and maybe the Southern Ocean too. So that's something that might come up. And then I think the other thing, one of the reasons that we're not sure the project, CSM project as a whole, has the resources for a large ensemble is that there's, I think, interest / pressure in higher resolution configurations of the model. So, you know, like if we want to run high resolution CESM, which I think would still be about 1/10 of a degree in the ocean sea ice, you know, that's going to take a lot of resources. And so I think there's just this balance of what people want. So I guess we're also interested in, just across the working group, you know, what's your interest in high resolution versus the large ensembles, or, you know, some of these regional configurations. Is that something, you know, that Dave and I should make sure that we're working? I mean, we're already talking to the Crocodile people some, but making sure that we have ways to do that for sea ice, or like you'd be interested in community simulations produced with that or something like that.
Do you want to say? Anyway, I'm pointing at you, Elizabeth.
Oh, you point mad.
Yeah. We've started a regional working group around this ice consortium, and we have several groups, mostly the sort of prediction, the operational centers.
Are really interested in
Yeah.
regional configurations of sites. where the boundary conditions are actually allow the ice to go in and out.
Yeah.
And so there's a little working group talking about that.
I should point out that the Crocodile Group, this is like an ice ocean model that's forced. It's a forced atmosphere, so it's not coupled. In theory, you could use reanalyses or CESM output to run it, but we don't. I think right now it's still kind of getting everything functioning, so that's not all in the capabilities yet. All right, so there's a consortium working group on this.
It would be good to maybe, as Crocodile evolves and this SICE working group evolves, maybe to connect the two a little bit.
Yeah.
Yeah.
Okay.
Yeah, I've been trying. I started that introduction, and the Crocodile group is having a workshop in October or something like that. And I think they were inviting CI's participation there. So.
Is there, hello, hi.
Hi, Auntie.
Is there anything going on regarding regional mesh refinement for the Arctic and or Antarctic? For CSM3, is this a big can of worms?
No, not so much. I mean, Adam's done a lot of work on the CSM. You want to say something about it, Christine?
I have a postdoc who's working with me, Kyle Nardi, and he's planning on using variable resolution with CSM3, and he has a beta version he's using now. So it is on the table.
Right.
I don't know if there's anything planned for the Arctic or Antarctic.
Right. And this is only atmosphere, variable resolution.
Yeah.
We haven't started trying to do coupled variable resolution at this point. So.
Yeah, there's also, the big effort at DOE for the 4-kilometer global model. I'm sure Elizabeth can say more about that. I know a lot of work is going on for that at PNNL, for example, SCREAM. But yeah, that doesn't have an ocean either. I mean, the ocean part always lags, right? Like, yeah. Anyway, I don't know. Yeah, I think it depends on people's thoughts about what's important, like the high resolution modeling with few ensemble members or tons of ensemble members, but going at it with lower resolution and knowing that you're going to miss certain things, right?
Yeah.
I don't know, like, has our community figured that part out in terms of what people like?
That's why Andrew just said he wanted to go to DOE because he can have both. He can have high resolution and ensemble members.
I don't know about the ensemble members. I've been talking to some folks at PNNL, and definitely they are burning core hours, running SCREAM, but I don't know if this kind of variability science that is possible with CSM is going to be possible at all with that model. It's just like at a certain point, it just becomes that the computational expense is so large.
I guess in terms of the community members, how much do you feel like you need really? I'm saying really high resolution, that's a very general term, but are you finding that, I guess in CSM3, our workhorse configuration is 2/3 of a degree, so it's slightly higher resolution than CSM2 was. Is that proving to be like an adequate resolution for some of the stuff you're doing, or do you feel like you really need more higher resolution simulations? Because part of the cost for us at NCAR is like people time to make sure that the high resolution simulations are tuned appropriately, and I don't feel like we've been able to do that so much in the past.
Yeah, my understanding in terms, CC says that the tripole grid is a big improvement. Okay, yeah, the 2/3 resolution, or 2/3 degree resolution. My understanding is that for SCREAM, one of the big advantages is that you get good resolution of MCS systems, as well as like hurricanes and typhoons. But obviously for polar people, I'm not really sure how that relates. So because I think kind of the synoptic scale systems that we're usually concerned with are, I don't know, maybe they're reasonably modeled at, you know, the coarser resolutions.
Well, I think there's also the question, mostly in the ocean, of, you know, higher resolution and which parameterizations are appropriate, and, you know, having scale aware parameterizations and things like that make it trickier at high resolution. You get really nice pictures and animations, but, you know, sometimes there's big biases in those runs that are problematic, so.
We did some runs with the Arctic grid, the refined mesh in the atmosphere for the Arctic, and I think it gets as fine as 1/4 of a degree. So, you know, it's still not fine. There may be different versions of it, but the one we were using, I was about 4 times as slow.
Right.
So, and then the other silly thing we did was we nudged in it. And it really, if you're going to nudge, resolution doesn't matter because you kind of overwhelm the solution by nudging.
That's a good point.
But, you know, it just depends on what you're doing. But
I just wanted to clarify that at least in the CESM project, high resolution refers to 10th degree ocean, 1/4 degree atmosphere, and ultra high resolution is, you know, more like 4 kilometer atmosphere. So just, so, you know, Hansi, you're talking about SCREAM, which I think is 4 kilometers. You know, we've been talking about that as high resolution. In the CESM project, that would be referred to as ultra high resolution. Just so people are aware, when we say high resolution, what we mean is like a 1/4 degree atmosphere coupled to a 10th degree ocean. And there is some emphasis on getting a model version like that for CESM 3, whereas that really wasn't done for CESM 2. You know, I mean, all the IHASP runs, for example, are done with a CESM 1 version of the model.
Right.
So there's going to be some focus on that high resolution version. The ultra high resolution, I think, is in CESM project case is kind of a more experimental thing, but there's interactions with SCREAM and, you know, some of the other stuff going on.
I know, Christine, you wanted to say something?
Well, I just wanted to clarify or add to Hansi's, you know, statement on what SCREAM can do. I know that it also simulates atmospheric rivers much better in the SCREAM. So for what that's worth, I mean, but that's more of a extratropical transition maybe into the pole. So it may not be as important. But it does do those types of synoptic systems better.
And I realized one thing that I didn't even list, but it's a set of experiments that are available that are in this high resolution category. I think these are the ones that Marika said are IHASP, but now they're called Mesa Clip.
Right.
They're all available, and I don't have the website ready, but I will send out like a very short list of the notes and I'll include a link to that. But I think there are like 10 ensemble members of this 1/4 degree atmosphere, 1/10 degree ocean ice that are available in the historical and I think in the future. And I think it's like Marika said, it's all CESM 1, so I think it's RCP 8.5. And we haven't actually looked at them a lot, so I don't know that the CIS even looks good. But if anyone in the working group wants to look at them more, they are available. They were kind of run. Yeah, I feel like that was a whole separate thing, but I can send out the link to that since I realized that.
Well, CC and I have looked at the original IHASP runs and not great in terms of sea ice.
Yeah, Courtney.
Yeah, just referring back to yesterday when we were talking about kind of community-driven conversations and work. I feel like something I've heard a lot from Laura's work and from others is high resolution being of value to communities. And I mean, if the model's incredibly biased when you move to high resolution, then that's not of value. But one thing we might want to consider balancing, I suppose, is what people seem to want from us, which might be high resolution than we think we want.
And possibly a way to thread that needle is like this crocodile project. Maybe you can have a higher resolution in a particular area and force it with CESM that's lower resolution, especially if I guess what Alec was asking, like, if a community cares about the next 20 years or something like that, you could do that higher resolution regional domain in that area of interest. If, you know, assuming you have a project or whatever to do that. But I think that could be a way to bridge this, but you would have to know that you're going to be missing other interactions that may be important on those different timescales. Yeah. Very good.
Well, I think the high resolution stuff, it seems to me like there could be a lot of work done using machine learning for downscaling. And so this just occurs to me, are there simulations people would like to have to use as training for machine learning kind of applications? And is that something that we as a project should be thinking a bit more about?
Right.
So, I mean, we might not be able to do, you know, a large ensemble at high resolution, but maybe we can do enough simulations that you can create a nice kind of downscaling, machine learning based downscaling that would need to rely on some high resolution simulations perhaps.
Right.
I was training.
I was going to mention that. It's too bad that Will left, but you know, but I think that's one thing that the CSM is also working on, bringing in more machine learning sort of methods and capabilities into the model. And so I think, you know, this is something, you know, we want more of with the CICE, you know, machine learning methods, and maybe that sort of goes into the CSM 3+ category. But I think, you know, that's, yeah, those are some good thoughts.
Yeah.
So CC, you had something?
Says regional Arctic with high resolution waves might be good for use with a machine learning parameterization development.
Yeah.
I expanded some of those words.
Yeah.
Yeah, it might be the only way we can run high resolution with waves.
Right.
Because they're so expensive. Just get rid of the rest of the globe. That's good.
Who needs it?
I mean, speaking of, you know, hybrid models that are partly physics, partly, you know, statistical AI, I think that, I mean, ECMWF has their AI forecasting system that is operational now. Like, this is the direction that I think things are going. If specifically, if you want regional information, for example, I mean, there's no way that you can run physics-based models at the resolution and frequency that people might want them to be run in order to produce operational forecasts and other types of operational data. Yeah, I think that like the writing is on the wall, especially now that we have, you know, the world's premier forecasting center having an official AI operational model. And I know that's only atmosphere, right? We have a lot of work to do, but I do think that something like that is in the future.
And I think there are some conversations, again, in CESM project, not so much in the Polar Climate Working Group, but about climate emulators. And so, you know, kind of similar topic. So,
or even, you know, like a final, like fine tuning layer or something where you take like coarse output and then, you know, you're able to use inference to produce like finer scaled output, for example. So it could be like some sort of hybrid system like that. Like, it doesn't have to necessarily be 100% AI. So, I mean, there's so many options for all of this that I think, especially if this is the direction of, in terms of just the kind of information that people want. I mean, you know, the other thing too to say is that, you know, like, sure, like we could use a supercomputer that was 10 times larger, but I mean, do we really want to do that? Just given the energy costs and resource costs of that? Like, I don't know. It maybe doesn't make sense. So I don't know, just things to think about in terms of like what's reasonable, what's needed for science, what's needed for like, you know, kind of the more science and society kind of mission driven work, and how to get resources for those different things and how to prioritize them and who does that work. Sorry, that was like a lot.
This is sort of going in a different direction off of Courtney's point about like science for society and stuff, but thinking about what kind of scenario might be useful to run if we're doing, well, not we, but if I'm not part of the Polar Climate Working Group community member here. But
You are because you're here.
You are
Never
now.
let you go.
but just in the sense of what kind of scenario might be useful to do a medium or large ensemble with. Both of the previous large ensembles have chosen very high forcing scenarios for reasons that are totally reasonable as far as like high signal to noise ratio, seeing what happens in the model, isolating these changes in variability, that kind of thing. But from a like impacts communication perspective, and I know a lot of other people have found that that's difficult, especially as like 8.5 in particular and 370 start to look maybe less likely in the context of like economic futures and that sort of thing. So maybe there's an avenue here for a moderate mitigation medium ensemble to be something new that is kind of adding a lot of value for community science.
I think along those lines, another project that you're reminding me of is one that are called the HOPE experiments. I don't know what the acronym stands for.
Highly optimistic PE.
Optimistic P
Prediction
something
ensemble, I
experiment.
think,
Okay.
but I was thinking if we did a large ensemble off of that, then we could call it hopeless.
I don't know how many people are highly optimistic at the moment. Anyway, but I can send out a link to that as well. Those are ones that I think they use CESM too. They have biogeochemistry on, and they have climate mitigation to try to see if we can, like
Right.
geoengineering, if there were geoengineering and there's negative emissions, what do those look like? And I haven't looked at them personally. Have you looked at them, Courtney?
No, but I know there are 5 ensemble members and they assume net negative emissions by 2030. And I mean, it's highly optimistic. And I think like a drop in emissions starting in 2015. And the cool thing is that the HOPE scenarios show a big divergence from the large ensemble within a couple of years. So
The Arise project was like another sort of not necessarily plausible, but like useful scenario. I guess I was thinking something more, I realize it's not the CMIP 7 scenarios, but something more like the SSP 245, but a large ensemble sort of thing.
There were
So, yeah.
these smaller ensembles that were done with the 1 degree, 2 degree C target things too. Ben Sanderson kind of led a lot of those too.
The Brace project. Yeah.
Race.
So I'll try to send out, when I send out like a thanks for coming to the whole working group. So if you're not on I assume you're on the working group email list if you're here, other than maybe you, Daniel. But I'll send out like a short summary of the meeting and try to include the links to those as well. We've been talking about this, I think, for like 45 minutes instead of 15 or 20, which is great. It's really good to get all this feedback from everyone. Does anyone have any last or a few things they want to bring up now before we talk a little bit about planned future developments? And then we can have like open discussion at the end before 4 as well. Last thoughts. CC, Hansi, anyone?
Yeah, one question regarding the ensemble size. So what's the minimum ensemble size that it's not even worth it? Like if you run an experiment, you have 1 member. Is anyone going to use it?
Or if you're talking high resolution, everyone will use it, you know?
I mean, I've been on a reviewer on papers on CESM, but where they have 1 ensemble member and they're trying to do something. And I'm like, how do you know that this isn't just?
Well, okay, maybe rephrase the question. Are they going to use it well?
Yeah.
I mean, I would think we were talking for the nudging runs. It's like you even in those, you want like 3, maybe 5, and then 15 to 20 is ideal. But I feel like other ones, like in the initial less melt experiments, I think Jen compared 5 ensemble members to the whole large ensemble. And because the large ensemble existed, we could say with more confidence with the 5 that these are actually significantly different than those. So I think if you have a large ensemble to compare to, you could still have an ensemble of 3 to 5 and maybe be able to say something useful. And I think depending on what your question is, you could just have a single run, like if you're wanting to look at processes, you can run a single ensemble member and look at those specific processes during particular events. You know, it's just, that's not giving you an idea of what's happening climatically, so.
Yeah. I think Alice made my point. It's just that that's the whole motivation for a large ensemble, is that we can produce that. We have the infrastructure here to do that. And so then that allows members of the community to go out and do smaller sets of experiment and have the large ensemble to compare against. So.
And this is Alec. I did kind of agree with David's comment earlier about, yeah, the need to maybe just explore some CI's parameters and generate some runs. And yeah, that can be useful training data. Even if, as we have just said, it's not, maybe just a single run isn't going to be climatically as insightful. I think it could be useful to feed into kind of training algorithms and understand, yeah, how parameters impact the CI state. And I think, yeah, that paper that was mentioned earlier by David, I think people still seem to cite that for understanding the impact of parameter perturbations for DA applications. And I think we could do with more of that kind of work.
I was just going to say, if you're doing a sensitivity study, you also, I mean, you can trade run length with number of ensemble members, right? And depending on the process, if it's something that changes relatively quickly, you know, integrating 20 years might give you enough,
Right.
you know, might give you enough signal to distinguish the difference, right? So.
Yeah, definitely.
Well, and adding on to, you know, something Elizabeth brought up, that we have this quality control test in the SICE consortium. So if we're talking about evaluating SICE variables, we can at least assess the parameter sensitivity within the context of that. And that's, you know, a 5-year run. And we can assess the differences between, you know, it's looking at ice thickness for 5-year runs. And so that would be relatively attainable, I think.
Are those forced or fully coupled?
Well, they're generally forced, but we can still use the output from fully coupled runs in the same way. So.
All right, I'm gonna I just have one more slide, and this is about kind of future plans for CESM 3+. Would you guys mind sharing again? All right, thank you. Okay, so earlier today, Dave showed that timeline of what has actually got into CESM 3, and there were a few things that were like, we planned to get them in there and then didn't. And I guess here's kind of what we're planning, and we want to hear if there's other stuff from the community that you'd like us to get in there, or that you think is important, or that you're working on that you want to get in there, something like that. So the first is the C-Grid capability. Dave worked a lot on this. I think it was.
What was a consortium effort?
I meant within CESM.
Yeah,
Yes.
yeah.
So the consortium did a lot with C-Grid. We've tested it in CESM, and then we were having some issues, so we kind of backed off it, given what's going on. But we're hoping to get that into a future, you know, I don't know if it's 3.1, 3. Whatever. So that's something we're working on. Improving the ice radiative transfer to match the SNCR model, the SNCR scheme that's in the land model. We talked about subgrid scale snow heterogeneity. We have talked, I think Dave said this for a long time, of coupling the sea ice biogeochemistry and the pelagic biogeochemistry. We actually were recommended for funding for that, but that's on hold until who knows what's happening with the federal system. So that we're hoping that will actually happen soon. And there already is sea ice biogeochemistry in IcePack. And so we're hoping to leverage that with existing Marble stuff and maybe add some polar specific functional types as well. I mentioned the regional ice ocean development that's going on, and then just kind of open mic for anyone else. I think, like I said, the things we want to know is like, how important do you think these are that we need to get these in soon? Are you working on them? And you can provide expertise, feedback, code, etc. That sort of information. Anything else you want that's not there?
What about waves?
We're gonna have waves in CSM 3.
You could improve the fracturing.
Yeah, but that's another good one, just improve wave fracturing.
Good to add to the list. Are there certain things on this list people feel should be prioritized? Courtney has an opinion on this, but
Full favorite. I mean, I guess along those lines, if there's something that you want prioritized, if you don't have funding, we should talk to you about ways to try to figure out a way to get it funded too. Melinda?
Can you expand on the subgrid scale snow heterogeneity? Like, what are the plans for that exactly?
Is this Lorenzo's parameterization that we're talking about? So,
Okay.
yeah, so Lorenzo has, it's a parameterization. It's basically a correction to the conductivity that accounts for the fact that you actually have heterogeneous snow on top of sea ice and not just a single snow thickness. So, you know, Lorenzo Zampieri, for those of you who don't know, he did a lot of work using observations from Mosaic and 2D conduction models, and David was involved in this work, and came up with a correction for the conductivity. And so the plan is to incorporate that into SICE. It just hasn't happened, in part because Lorenzo left NCAR and went to ECMWF and is doing, I'm sure, wonderful things there. He's a wonderful scientist. But it's kind of been, you know, so we need to kind of see that through here at NCAR with his input. But so it kind of falls on Dave, and Dave has lots of things on his plate. So that's why it's not in CESM3. But that, so I mean, there's a lot more that could be done with snow heterogeneity. This is just one small piece of how, you know, heterogeneous snow impacts the sea ice system. Like there could be albedo parameterizations associated with snow heterogeneity and things like that. So, but yeah, this is just that conductivity.
Okay. I would definitely advocate for looking at radiative effects of snow heterogeneity as well.
Yeah.
Or including that.
Like David wants to say, I don't know. You had this motion where I was like, David's gonna say something.
I guess just in case people are worried about the subgrid heterogeneity impact on thermal conductivity, the just general uncertainty in case snow, like the material property case snow, is also fairly large. So it's, yeah, just as, I mean, if you're, I guess, when you're thinking about improvements, that's also would be in the same category as like, so that should be improved, but it's been hard to observationally constrain. And it's kind of a similar thing with the subgrid scale heterogeneity. Like we could measure it for Mosaic or for individual campaigns, but it's the generalization's hard.
Yeah.
So
I guess along those lines, stuff that's happening at DOE, like Andrew Roberts is trying to do porosity work, and that could affect, you know, density if you're thinking about that. And it could affect biogeochemistry and ridges and things like that. But I don't think that's an immediate thing we're trying to get in right away.
Yeah.
And I know, David, you looked at snow redistribution around ridges also. So I don't know if that's not the same as Lorenzo's snow heterogeneity thing, but I don't know if it's anything you thought about also.
yeah, that's in the plus. Okay, that's the 3+ category side of things. But yes, I'd love to do more of that. I mean, the part of the challenge there is you need a better representation of the surface topography. You need both a better representation of what is the ridge sail geometry distribution, et cetera. And there's some parameters related to snow erodibility that are quite observationally variable. That you, so, yeah. Can I actually ask a question about the second one here, the Snicker?
Yeah.
One. Do we have? I guess I'm wondering about the motivation for this, and is this just to better match the land model, Or do we have like a clear science need
I,
that the 3-band is not achieving?
I think there's definitely some evidence that the 5-band improves the simulation, but I think a lot of the driving motivation behind this is that the atmosphere is 15. and we're, and we're bringing that down into 3 currently. So I guess, there's some motivation there to suggest that maybe we should be improving that. And is 5 enough? I don't know the answer. There's been a lot of work in E3SM on this, but.
Yeah, but as far as that one goes, that is already available in IcePack, so it's a matter of validating it. in
Exactly.
CSM.
Yeah, exactly.
Writing the parameters.
Yeah, we don't need to add any code. But that brings up an interesting point that, sites consortium development is continuing and there's contributions from all around outside of this community. Form drag, for example, things like that, that we haven't even been thinking about yet. So, are there other things, beyond this list that are already in SICE or going to be in SICE in the near future? Marika.
Landfast ice isn't on this list.
That's right. Landfast ice is not on this list.
There's a parameterization in SICE.
Yeah.
No, I'm just wondering if that would be a useful thing for people, even at these course resolutions. I mean,
Right.
the 1 degree model version. There's nods, okay. So maybe it should be back on the list.
It wasn't an intentional, missing it.
I was going to add, we've got our new MELT project starting up with Chris and Maddie, and so pretty interested in this new sea level scheme that David's contributed. Keen to see what that looks like, and thinking about maybe how that might compare to the kind of topo scheme that my old colleagues at CPOM produced, and maybe ways we can think about that kind of melt pond representation more explicitly instead of just impacts on sea ice, but the actual representation of melt ponds across both hemispheres potentially. So generally interested in that is all I wanted to say. And actually, has anyone looked in these kind of new runs? How does have you looked at the melt pond fractions or anything? Or it's just been the sea ice state so far?
Yes, I presented this morning on. But
So I did know. I was looking back through the slides. I didn't see.
Where I was zooming through. And I don't think I may not have put a pond fraction slide. I mean, it's as you'd kind of expect from the parameterization. It's average of around 30%. Pond fraction, a little bit higher in the marginal seas where effectively the ice is thinner and you can more easily the dynamic equilibrium of like melt versus drainage ends up with a slightly higher pond fraction. But 30 to 40% probably in on average.
Nice.
So I'll say, I think the biogeochemistry should be a priority, even though Courtney didn't say it. And partly it's been on the list for such a long time. And I think we're doing a lot more polar biogeochemistry work, and which I think has been really, really valuable and interesting. And so we're now using the model to look at, marine ecosystems. The fact that we aren't using the sea ice biogeochemistry is just so sad. So
And
So
I actually started this coupling, I got a fair ways with it. It's not all that difficult to add coupler fields. But the main important thing is we need to do those experiments. We need to have people in this community looking at. So.
All right, I think just open mic, any topics that we've talked about, either community experiments, developments, anything else, science for society that came up yesterday. who you think is gonna win March Madness. I don't know, whatever. I don't actually call it March Madness, but anyway, realize it's March.
I had a very quick question because I saw, yeah, Elizabeth's here. What's happening with E3SM and CMIP 7? Are they submitting?
The plan is to submit the absolute minimum. That is so that the community has a chance to look at E3SM. It provides some credibility for E3SM. But I don't think they're planning to do a huge campaign.
Mhm.
Andrew told me you're just doing deck, basically.
Yeah, just deck.
Okay. Yeah, I was just wondering about into comparisons, but cool, thanks.
David?
I guess I have a topic in the plus or maybe plus category. But I wonder about sort of with the future of the CIS model development, us running into this kind of curse of dimensionality where, right, we currently have an ice thickness distribution and now there's a joint distribution with flow size, and soon there will be a further joint distribution with macro porosity. And then if you wanted to add a variable snow cover or, independent thermodynamic columns under ponded ice versus not ponded ice, we're getting to, and once we're past 3 dimensions, I can't get my hands around it anymore. And so I guess I mean, this is in the plus category, but should we be starting to think about how we can represent the diversity of sea ice in these models without ballooning like computational and storage costs?
AI.
AI is the.
It's the solution to everything, isn't it? I would say for some of these things, we want to parameterize them as opposed to, like we've talked before about within our thickness distribution, having sub-column, thermodynamic calculations. And I mean, then you just have more thickness categories in a sense. You have to lump stuff back together at some point. But I think we can parameterize some of these effects for a climate application, which I think is like what Lorenzo's approach to the, conductivity correction is, right? You're not explicitly simulating heat transfer through the heterogeneous snow, but you're correcting for the fact that heterogeneous snow affects your thermal conduction. So I think we need to be smart about how we parameterize these things too, but some of these things we haven't really, really maybe done a good job at, or we could do better. I think especially in the subgrid scale kind of heterogeneity realm.
Well, and I think too, this idea of higher resolution too, that hopefully we're resolving more as we go down in resolution. And, and yeah, I agree with Marika though, that it sort of does become a point where it's not sustainable to just represent, PDFs of absolutely everything in the model. And, I've already been talking to Letty about trying to reduce the wave frequencies. We're getting 25 wave frequencies from the wave model, and we don't really need that for a wave fracturing scheme. So I think as Marika's highlighting, we just need to be careful about how we parameterize these. So.
David and I had a fun conversation about this weekend, and I thought he had some really cool ideas about how to limit the number of distributions to maybe actually have just a single distribution that has different categories, for lack of a better word, that define a number of different qualities that basically are the most different among the distributions. Like, thickness may be one of them, but maybe it would be snow depth too, right? So you would then merge categories when they become more alike in some kind of objective way. Anyway, it's something to think about. It would be a really big change to the code. But at this point, I think, Dave was saying also the slowest part of the model is just dealing with all the variables, the bounding of all these distributions. So you can definitely say that, explain it better than me, Dave, but the alternative is to figure out how to do that faster, because it's not parameterizations is I guess my point, that it's slowing us down. It's actually just dealing with a gazillion variables.
And I think like clever rethinking of some of these things is great. And so, David, you have ideas of clever, I mean, seriously, I think we don't need to be bounded by what we've done in the last, since Mayhood and Untersteiner wrote their thermodynamic model back in 1970, whatever it was. Anyway, like, I think, we can rethink all of these things. And I'm sure there's clever ways that, so dream away.
I mean, Melinda's first visit here a few years ago, we talked a lot about the subgrid scale heterogeneity of snow fraction and the way we parameterize that in the model. And, amazingly, we just played around with some things. We found this hyperbolic tangent curve that actually fit the data extremely well, except for where it didn't. But I think that the problem is that never got in. We did some tests with it. We tried it out, but it just never made it back in. So, yeah, just getting people engaged and working on these things, and
I know we don't have a lot of time left, but I also wanted to just bring up the topic of diagnostics. So as Dave mentioned, there's this Cupid diagnostic package that is being developed, and there's part of the effort for that is kind of a quick look model development package, like this is a showstopper, or this run looks better. Right now, everything we have in there is ice area, snow volume, ice volume sort of metrics. They're pretty basic. And I think there's a lot of room for improving that. And just some of the talks we've seen in the last couple of days, people have put up slides which are like, oh, that would be a nice metric to have in there. So, and I think back to some of the CESM2 papers, like Melinda, you have these beautiful snow, comparisons from CESM2. Those kinds of things could be really nice metrics to include in this diagnostic package. And so I don't think we're going to sort out in the next 8 minutes what those diagnostics are, but I just think if people in this community would be willing to share some of the cool diagnostics they've developed, and we could incorporate them into this package, which would be a publicly available thing, that could be really useful, both for people in this room, for us developing the model, and for the broader community too. So, like your SAM metric, and I mean, I think we've seen a lot of nice examples, and anyway, just a plea, and maybe we try to coordinate this through the working group a little bit more.
For some of those, we talked this morning, it was not just this morning, about manuscripts too. Like if, it could be that as part of that process, for comparing against the ISAT2 thicknesses that Alec presented earlier, maybe that's something that we can incorporate into that somehow, and snow stuff like Melinda talked about. So yeah, melt pond fractions.
Is there a Git repo available where people can go commit code for some of this? Like if you have diagnostics?
I talked about it earlier. Yeah. So.
Okay.
Yeah.
You have, there's a link somewhere.
Yeah. So we've been doing this all in Python notebooks. So ideally, adding in additional notebooks would be wonderful. But again, just talk to me, and I'm happy to get you going with that.
Would it be useful to just send an email out to the working group with that information, or does it need to be more controlled, or?
Yeah, is it a public repo?
Yeah, it's a public repo.
I think I can add it to the link with the other, like, basically.
With the post workshop email. Yeah, it was also in the presentation earlier, but yeah.
Yeah, it's definitely on our list to take a look and try and engage with that.
Yeah, and as an additional piece to this too, I mean, back to the experiments and getting runs done, and I know that the data management part of these simulations could be a huge burden. And so, you know, again, please come talk to me if you need some help setting up your experiments, post-processing the data sets, you know, whatever you need, you know, just that's.
Anything else? We technically have 4 minutes left. I feel like people are like, all right, well, I think we can adjourn 4 minutes early. Thank you all for coming, for being part of the discussions, presenting your great work. I really like seeing what everybody's doing. So I find that really exciting.
Thank you for organizing.
Yeah. Yeah, we wish you guys online could join us at Southern Sun.
Yeah.
So.
I know.
Okay.
Next time.
Next time.
Until June, which June is the 30th CESM
Oh, yeah.
workshop. So there will be some special activities and you'll hear more about that on the email list soon.
Thanks for organizing, everyone.
Thank you all. Bye.